Yes. Good afternoon, all of you. So first clear the video and audio for all. Okay, right. Okay. In the last class, we started losses in transformer. In losses, mainly two major losses we have. What are the major losses we have? Copper loss and iron loss. So first we have seen copper loss. Copper loss due to the resistance of windings, primary and secondary. Whenever there is current in the winding under load operation, because whenever load is connected, then only magnitude of current is high. Otherwise, under no load condition, if you talk, there is a current only on primary, that is called no load current, which is very small. That current generally we neglect, a small current. So small copper loss, that is negligible. But only under load condition, the current's magnitude is more on both primary and secondary. Then there is an I square R loss, that is we call copper loss. Now there we have seen how to find copper loss at different loads, different fraction of loads, maybe at full load condition or half full load or 70% or 80%. At any fraction, how to find, we have seen one equation there. Okay. And also we have seen how to find per unit copper loss. How to find per unit copper loss? Full load copper loss by volt ampere rating. The rating, whatever rating on the nameplate is there, that is we substitute into that is per unit, and if it is percentage, multiply with 100. One important equation we got previously, what is that? Percentage copper loss of transformer is nothing but percentage resistance of transformer, or per unit copper loss of transformer equal to per unit resistance of transformer. Anyone, both are same one. Okay. So that is regarding copper loss. That is a variable loss. Why it is variable? Because it depends on current variation. Current in windings is not fixed, because when load is changing, current in windings also change. So accordingly, our I square R loss will change. So that is a variable loss. But this iron loss is a constant loss. Now, still we did not complete totally that iron loss. Only the one part of iron loss is what? Hysteresis loss we have seen. What is the hysteresis loss? It is due to magnetic material. It is due to magnetic material, that is whenever the magnetic material subjected to time varying flux or alternating fluxes simply, then the dipoles of the material will change the orientation, means direction. They will align in different opposite direction for every positive half cycle, negative half cycle. So due to that, these dipoles are consuming a small power while changing from one direction to other direction. They will consume. Now that is the power consumed by dipoles, but for us that is loss only, no, some loss for us. So that is hysteresis loss we treat. Okay. Now to that hysteresis loss we can find by two ways. One is, I said, graphical method, and other is this one, mathematical method. So using graphical method, how to find? First we need to find the area of hysteresis loop. For the given material, we have BH loop or hysteresis loop. Calculate the area of that loop. Once you know the area, multiply with the supply frequency, you will get total hysteresis loss. That is one way. And second method is this mathematical, using equation. So this is given by one scientist, Steinmetz. So using this equation, we will find what is the hysteresis loss, total hysteresis loss. Okay. Now, before going to this equation, so I will give one small question. Previous year in the previous gate, one of the year, we have the question on graphical method. Only 1 year we have the question on graphical, and remaining all, mostly in every gate examination, mostly we have question on mathematical method only. In only 1 year we have the question on graphical. So let's see what is that question. Read the question. Read the question. WH is what? Hysteresis loss. We are considering as WH. No. Harshavardhan, check net connection. Everything is okay. Check from your side also once. So whenever anything audio video is little breaking, you need to check from your side also once, because from this first point mostly more so many people are watching, no? So getting one or two students problem is that is from your side only. Okay. Yes, I will show you. I will show you. The hysteresis loop or BH loop of a magnetic material has an area of 5 centimeters square. So the BH loop or hysteresis loop, its area given directly. The area is area of hysteresis loop is 5 centimeters square. So you can write it is 5 centimeter into centimeter square. No, with the scale given as 1 centimeter is 2 ampere turn, and the other centimeter is, that is x-axis 1 centimeter, y-axis 1 centimeter. So that values they given here 50 milliwebers. So actually we draw BH, B on y-axis, H on x-axis. Okay, and B proportional to what? Flux only, no? B means flux per area. Area never change, flux is the variable. And in the H axis, that is x-axis is having H term, field intensity. H is proportional to H. What is H actually? MMF per unit length. Length will not change. MMF may change. So MMF. So H proportional to MMF. That MMF is 1 centimeter, 2 ampere ton. MMF ampere ton. And y-axis is flux. That is 1 centimeter is 50 milliwebers. Area given 5 centimeters square, means x-axis 1 centimeter, y-axis 1 centimeter, total centimeter and centimeter I'm writing. So in place of this centimeter, 1 centimeter, substitute these values, you will get area of one loop or area of hysteresis loop. But we need to find total hysteresis loss. What is total hysteresis loss? Total hysteresis loss. First calculate this area, how much? 5 into 1 centimeter is 2 ampere turn, and other centimeter is 50 milliwebers. 50 into 10 power minus 3 webers. Okay, and this is, calculate how much it is. This is getting, calculate this. This is 0.5. Area is 0.5 meters square. Okay. Now we need total hysteresis loss. What I said, the total hysteresis loss with respect to graphical method is what? Area of loop. Area of loop we calculated. Multiply this is with supply frequency. Area of BH loop or hysteresis loop multiply with supply frequency. What is the supply frequency? 50 hertz. So 0.5 into 50. So this is how much? 25. So this is the total hysteresis loss from graphical method. Okay. So to find the answer using this method, you should know the area of graph, area of that loop first. If they given area in the question, easily you can find. Otherwise, if area is not given, you cannot calculate hysteresis loss, because that area is uh, not a particular shape area, that is a non-linear shape, so which is difficult to calculate. Okay, that should be given, then only we can find. Ampere turns. 1 centimeter is 2 ampere turn. 1 centimeter is 2 ampere turn. That is h-axis now. One is h-axis, field intensity. Field intensity proportional to mmf. What is the units of mmf? Ni, ampere turn. And what is units of flux? Webers. So that is given in milliwebers. Okay. Now come back to the previous mathematical method. This is using mathematical method, the equation we have to find hysteresis loss. In the same way for eddy current loss also, we have one equation. These two you should remember. Now, in this equation, observe eta. This eta is a Steinmetz coefficient. This is a fixed value. It never change. Based on the material, it will be fixed. They will give in the question about this. And flux density. We know flux density proportional to what? Proportional to V1 by F ratio. It will change. When you change the voltage or when you change the frequency, density will change. So this is a variable. And volume of core. So once the construction is complete, is the volume of core will change? Never. So volume of core is constant always. And frequency you can change externally. Okay. Then how many variables are there totally in this equation? Two variables, flux density and frequency. So now we will consider two cases. Two cases. Case 1 is flux density is constant and case 2 is flux density is variable. Then what happened and how the variations we get in hysteresis loss, we will see. From these two cases only 100% you will get the question. 100%, no doubt. No other questions we have in this iron loss. Only from these two cases. The only thing is you should identify which case is given in the question. Okay, right. Case 1. So we have hysteresis loss WH equal to eta B max power 1.6 x value is what? 1.6 into V into F. So based on this we have two cases. Case 1, if I'm considering flux density is constant, Bm is constant. So when flux density will be constant, we know flux density proportional to what? V1 by F ratio. So if you keep the voltage to frequency ratio constant, so how to keep and all you will understand in numerical what it is, how to find these values. Okay, easily. This is case 1. V1 by F is constant, then only flux density constant. Okay, now already eta constant, volume constant. Now density also we taken constant. Now what is the only variable? F. Therefore hysteresis loss proportional to only frequency, remaining all constants. Whenever any value is constant, just remove that and take proportionally the variable WH proportional to F. Now I'm removing this proportionality and taking one constant AF. Let it is equation 1. Okay, hysteresis loss equal to AF. By removing proportionality, some constant is taken. Next, similarly, case 2. Case 2. If now I will take density is variable, Bm, maximum flux density is not equal to constant. Is not equal to constant means V1 by F ratio is not constant. Okay. Now what happened? Eta constant, volume always constant. Now density variable and frequency also variable. So two things are variable. So let's take the two things here. Therefore, WH proportional to Bm power 1.6 into F. Eta constant, volume constant. That's why we are not taking that. Okay. Next, it is proportional to Bm means what again? V1 by F ratio. Bm is proportional to V1 by F whole power 1.6 into F. So if you simplify this, V1 power 1.6 divided by F power 1.6. So totally you will get F power minus 0.6. Okay, F power minus 0.6 you will get. That's therefore WH equal to, I am removing again this proportionality, taking constant A V1 power 1.6 F power minus 0.6. F power minus 0.6. Let it is equation 2. So don't leave these numericals. Don't leave this iron loss numericals. 100% in every examination, one question, either for 1 mark or for 2 marks. If it is gate examination, if it is competitive examination, 100% one, either one or two questions will be there on this iron loss only. That much important. So these problems also related with respect to OC test. So when we go, next topic is test on transformer. In the OC test, there also you will get again calculation of this iron loss. Okay, it is not only here, in test also you will see about this loss. Very important. Okay, two cases we have. Now let's see some small examples questions. How we get question on iron loss topic. This hysteresis loss particularly. Write the question. So why I am taken 1.6 here? In the previous case itself, I given what is the value of X for silicon steel 1.6. Read the question. Read the question. A 10 kVA transformer. A 10 kVA transformer has any hysteresis loss of, has a hysteresis loss of 100 watts. 100 watts at 200 volt 50 hertz frequency. At 200 volt 50 hertz supply. At 200 volt 50 hertz supply. What is the hysteresis loss? What is the hysteresis loss? Hysteresis loss at 160 volt 40 hertz supply. So there is a transformer initially operated at 200 volt 50 hertz. Supply given is voltage supply 200, frequency 50. At that time the hysteresis loss is 100 watts. Now same transformer again connected to, now new voltage new frequency. Voltage is 160, now new frequency is converted to 40. Then what will be the hysteresis loss? Okay, now in all these losses, maybe hysteresis loss or eddy current loss or total iron loss calculation, what you need to check in every question, only one thing is you have to check V1 by F given in both cases is same or not, or same or different. V1 by F. So what is V1 by F initially? 200 volt 50 hertz. What is hysteresis loss in the first case? 100. Now what is new voltage? 160. What is the new frequency? 40. Now we need to find what is the hysteresis loss. Check the ratio here. What is this? 200 by 50, V1 by F, 4. And 160 by 40, voltage by frequency. Now what is this ratio? Now also it is 4. Means V1 by F is same or not? Yes, same. So which case it is? Case 1 it is. Case 1. Now observe case 1, hysteresis loss proportional to only frequency. Now utilize this relation. Utilize this relation. WH proportional to frequency. So as it is case 1, WH proportional to frequency. Using this, I am writing in two cases. WH2 by WH1. equal to proportional to frequency, new frequency by old frequency. So calculate hysteresis loss. WH2 is, already we have WH1 100, new frequency is 40. This is F2, this is F1. So F2 is 40 and this is 50. So the answer is 80 watts. So the hysteresis loss little reduced, 80 watts at a voltage of 160 volt and frequency of 40 hertz. Simple, easy questions. The only thing is these two cases you should remember. If you forget about these two cases, you cannot solve the further. Yes, right. So here you should not see only voltage or only frequency. What I said, you need to check V1 by F ratios. Every time V1 by F ratio, not only voltage. Okay. And Usha, you are getting doubt. This is live or recorded video. Now you may understand. Okay. A not required. See, maybe WH equal to AF. If you utilize what happened? A same constant. Na? A means constant. So if you write like with respect to WH equal to AF, what happened? WH2 by WH1 equal to AF2 by AF1. Anyhow, A cancel. No? That's why we are not taking no. No need of this. So at some equations or at some questions, we need to use that A also. Here A, in eddy current loss, we take one more constant B. So you will understand after completion of total iron loss where to use A, B, everyone. Okay. Yes. American transformer has low hysteresis loss, right? Like that also you can find. If you are able to find A value, then that is also right. Next, one more question. See, next one more question. In the above question, in the above question, what is the hysteresis loss? What is the hysteresis loss at 240 volt, 60 hertz? Now calculate this. What is the hysteresis loss at 240 volt, 60 hertz? So not 240, change this is. Let's take at 300 volt. At 300 volt, 60 hertz. 300 volt, 60 hertz. Manish Kumar, your doubt is okay. That is why we are not using 60 hertz like American frequency, because already system is established here. With 50 hertz, already system is established. Now, if it is required to change from 50 to 60, now you need to throw out all your home appliances mostly. Is anybody will accept this? No. We can convert now easily. 50 hertz, we can make 60 hertz generation, everything. But the whatever we are designing, the electronic equipments, everything, we need to throw out, particularly motors. Because if frequency increase, all your motor speeds increase. But motors are designed for some speed. The bearings, whatever design construction is there, that is with respect to 50 hertz. Now everything we have to change. That is difficult for us. Yes. See now, same for the previous above question only. Uh, what is the previous question? At 200 volt, 50 hertz. Initially, 200 volt, 50 hertz is there. Then hysteresis loss is 100 watts. Now the question is at 300 volt, 60 hertz. What is the hysteresis loss? This is we need to calculate. What we have to do? Again, same. Check V1 by F. Same or different? What is V1 by F here? 200 by 54. And what is V by F here? 300 by 65. So same, no? It is same or different? It is different. So as V1 by F is not equal to constant, which case it is? Case 2 now. Now go to case 2. In case 2, what is the equation? WH proportional to V1 power 1.6 F power minus 0.6. Okay, use this equation. Use this equation. In two cases, write the equation again and solve. Same procedure. WH2 by WH1. Initial voltage V12. Second case, previously V11 whole power 1.6. F2 by F1 whole power minus 0.6. So just two cases we applied using this equation. This is V11, this is V12, this is F1, this is F2. Substitute all the values. WH2 equal to 100 into what is the new voltage? 300. Previously 200. 1.6. New frequency 60. Previous frequency is 50. Whole power minus 0.6. Calculate this value how much? Yes, 171.48 or 5. So do calculation carefully, because if you miss the one power 1.6 or power minus 0.6, in place of minus also if you don't take, your values may change. 171.5 watts. So this is answer 171.5. Okay. Yes, right. Most of you right. Okay. So V I changed. Initially given 240. Without calculator, you cannot do this. Calculator is must. This is for gate only, no? For gate it is. For engineering services, if they given also based on options, you need to go. If you are not able to find directly without calculator, no, then approximately we can answer by observing options approximately. Okay. Now I will give two points, important points based on these questions, because these questions you may get numerically or you may also get theoretically. Like they will give directly in competitive examination like this. In a transformer, by keeping voltage constant, if the frequency decreases, what is the hysteresis loss? Increase, decrease, remain same, none of this. So this type of questions. So any question, that may be theory question or that may be numerical question, anything you can easily answer. Only the thing is you should remember two cases enough. From these two cases you can answer any question. Increase, decrease, remain same. This type easily you can answer. So I will tell you. First write the point. Make a note. 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 Right. First point. First point. By reducing both voltage and frequency, by reducing both voltage and frequency such that V1 by F equal to constant. V1 by F equal to constant. Then the hysteresis loss WH. WH means hysteresis loss. The hysteresis loss is dash. Increase, decrease, remains same. What is the answer? By reducing both voltage and frequency such that V1 by F ratio constant. What happens to hysteresis loss? This is our first example. Observe the question. This one, first one. Here we have reduced voltage 200 to 160. and frequency also reduced 50 to 40 such that V1 by F is constant in both cases. Like that we reduce. Then what happens to hysteresis loss finally? 80 watts we got. Okay, previously 100 watts, but now 80 watts. Now hysteresis loss is what happened? Reduced. So that point you have to write. Hysteresis loss is reduces. Hysteresis loss reduces. Next, second point. Second point. By keeping voltage constant, by keeping voltage is constant, if frequency increases, if frequency increases, then the hysteresis loss is dash. The hysteresis loss is dash. Increase, decrease remains same. Increase, decrease remains same. So you no need to remember these statements because learn subject but don't by heart the subject. If you by heart these points, definitely at some situation you will forget this, but don't by heart, don't remember this directly. Easily you can answer. So what you have to do is observe the question, observe the second point. By keeping voltage constant, actually V1 by F we have to check every time. Voltage is saying constant, and what is the frequency? Increases. Frequency increase. Now what is the flux density? Constant or variable? Definitely Vm proportional to V1 by F. Voltage is same, no change, but only frequency increase. Then flux density decrease. So this is what case 2 now. V1 by F is not constant, case 2. So in case 2, what is the equation? WH proportional to V1 power 1.6, F power minus 0.6. And that minus I am taking in the denominator. So directly I can write F power 0.6. F power minus 0.6 or divided by F power 0.6, both are same. Okay. Now apply here the change given in the point. What is that? Voltage is same, fixed, but what is the frequency? Increases. Then what happens to hysteresis loss? As denominator part is increasing, hysteresis loss decreases. So the answer is decreases. Hysteresis loss decreases. Suppose in the same question frequency decrease, then hysteresis loss increase. Okay. The previous first point also you can answer like this itself. No need of that example you need to see again. How voltage reduce, frequency reduce, such that ratio is what? Constant. First case. In first case, hysteresis loss proportional to frequency. No. So what is the question given? Both voltage and frequency reduce. So that should be there. Both voltage and frequency reduces such that, okay, both voltage and frequency reduces. So as frequency is reduced, what happens to hysteresis loss? Also reduce. Clear? So every point theory question in these losses, you have to go directly to case 1, case 2. From the equation point of view related, directly you can say what happens. Increase, decrease, remain same it is. Okay. Hmm. If both increase such that V1 by F constant, both increasing is frequency increasing, no? So WH proportional to F. As frequency increase, hysteresis loss also increase. Okay, that you need to analyze from equation what is given in the question or statement. Okay, so don't blindly remember these points. Just I given some example like this type of questions we are getting. Anyway they may give. So I given 2 points and they may give here. By keeping frequency constant, supply voltage decrease. By keeping frequency constant, supply voltage decreases. What is hysteresis loss? Second case it is. By keeping frequency constant, voltage only decrease. Now second case, WH proportional to V1 power 1.6. As voltage reduce, hysteresis loss also reduce. Or by keeping frequency constant, voltage increase, hysteresis loss also increase. Like this type of many combinations you may get. So I don't give all these points because it is not good to remember the points directly. Just remember two cases enough. You can answer any question from these two cases. Okay. Shiva, you are asking how we can operate at any frequency. The frequency is your supply. Okay, you are giving supply to transformer with different frequencies. Practically, these are all we don't have. In if it is required to operate, then what happened? That is, we are calibrating. That's it. But what is the frequency throughout India? We are operating the transformers are same 50 hertz only. No, these are just variation. We are checking what happens about losses. That's it. Okay, so this is about hysteresis loss. Now see the second one, eddy current loss. Second, eddy current loss. So already we have seen about this eddy current loss in the construction of transformer core. Okay, so let's see here the definition of this. This is indicated as WE, eddy current loss. WE means eddy current loss. Yes, it is due to what? The presence of eddy currents or circulating currents in the core. So why currents are circulating? Due to alternating flux passing through the core. Suppose taking solid core first. Solid. Let the core is solid. If the core is solid, whenever alternating nature of flux is passing through the core, alternating flux it is. Flux is alternator. Time variable flux. Now this core is having some conductivity or not? Yes, there is some conductivity, but not a good conductor, but there is a conductivity. Not zero, it is zero. Insulators will have zero conductivity. Is it a insulator? No. Steel, it is a steel. So conductivity is there. So according to Faraday's law, whenever a conductor cuts the flux or flux cuts the conductor, EMF will induce or not? Yes. So in the same way, in this steel structure also, some small amount of EMF induced. It in the core. That voltage you cannot measure. You cannot measure that voltage. Inside the core, there is some voltage. Okay. Due to that, whenever the core is solid, more surface area available, then currents will circulate throughout the core. Throughout the core, the currents will circulate, and these currents we call here eddy currents. Now, whenever there is a flow of current in any body, some resistance is offered by everybody in here. Everybody will offer some resistance, not zero resistance. Everybody will offer some resistance. So there is a eddy current, and resistance offered by the core to the flow of that current is let R say. So during that, an I square R loss. Don't confuse that. This is a copper loss. Only in windings. Only in windings. The I square R loss we call copper loss. And other than windings, we call here, particularly in core, we call eddy current. And if any other parts it takes place, we call stray losses. That is stray. Other than core and windings, wherever any other loss is taking place, they are stray losses. Okay, this is an I square R loss taking place in the core called eddy current loss. Write the statement of this. Due to conductivity of core, due to conductivity of core, whenever alternating flux is passing through it, whenever alternating flux is passing through it, it causes a circulating current called eddy current, which causes an I square R loss, called eddy current loss, loss. So can you measure this loss directly with any meter, like power measurement by watt meter? Can you measure this loss? No, this is in iron structure, we cannot measure this. Okay, for this also we have one mathematical equation, using that only we can find. So this is eddy current loss. Now how to reduce this eddy current loss? How to reduce this? How to reduce the eddy current loss? Already we have seen in the construction part. So we have two methods to reduce eddy current loss. So there already one method, two methods itself we have seen, but I said directly one method, like laminating the core. One more method is there, already you know that, but you don't know, because of that we are adding that. So what it is, observe. This loss can be reduced. This loss can be reduced by one method. First method is laminating the core. Laminating the core. Laminations. So if you make a number of thin plates, not single solid piece, number of thin plates, and attach it together, then little cross section is reducing. Due to that, eddy current magnitude reduce, loss also reduce. Our overall heat in transformer core is reduces. So that is one method, laminating the core. And second method is adding silicon. Adding silicon to the steel. So there directly we have, I said, like we are using silicon steel in transformer. Silicon steel directly we have, I said, but there I did not mention why we are adding that silicon. So I said about iron, then steel. What is steel composition? Iron plus carbon, small amount of carbon. And what is silicon steel? Steel plus a small amount of silicon, I said. But the main reason to add that silicon is to reduce eddy current loss. To reduce eddy current loss. That's why we are adding silicon to the steel. Otherwise, we should use only steel material. But we are adding small amount of silicon to that. So completely it is called silicon steel. And here the important is how much silicon should be added. This is also many competitive examination question. Percentage of using, that percentage of silicon is 4 to 5%, very small. 4 to 5% only. Suppose total steel is 100%, in that 4 to 5% is silicon, and remaining 95% is steel material only. Very small amount we add. Why we are adding is, if you add silicon to the steel, mainly the conductivity of the steel little reduce. Conductivity will reduce. For that reason we are adding. Once conductivity reduce, the magnitude of current in that body will reduce or not? Yes, reduce. Current magnitude depends on what? Conductivity mainly. If conductivity is high, more current can flow. If conductivity is less, less current. So due to this reason, we are adding small amount of silicon. You should not add more than this. Maybe people will get doubt. What happened? What happened if you add more silicon? If you add more silicon, more conductivity will reduce, but It will affect the actual properties of magnetic material, that is steel. Actual properties like high permeability we are using, low reluctance. So these properties may affect. That's why more than 4 to 5% we should not add. Okay. Now, which method we are using to reduce eddy current loss? Which method we are using? Because mostly people will tell laminating the core. So we are using both silicon steel we are using and laminations also we are using. Both we are using to reduce eddy current loss effectively. Okay. Yes, very good. Gomati Shankar. Yes, very good. Gomati Shankar said what it is these eddy currents will produce a flux opposite to main flux? Yes, definitely. See here. Suppose this is a core. Observe carefully. This is a not transformer core. Some piece of the core I'm showing. Okay, not complete transformer core. So let this is a small piece of core. Transformer core. A small piece, limb or yoke, anything you can assume. This is I'm showing. Now consider main flux is passing in this direction. Main flux it is. This is main flux. Okay, main flux is going in this direction in the core. Now what is the reason for eddy current? The alternating flux in the core only. Now that is main flux. Whenever flux is passing, it causes EMF, it causes current, that is called eddy current. Due to that, some loss. Now whatever these eddy currents are there in the core, it will affect main flux or not? 100%. It will affect 100%. These eddy currents will affect a little reduction in the main flux. How it is? Same according to Lenz law. Everywhere Lenz law is satisfying. Effect oppose the cause. What is the cause for the eddy current? What is the cause for this? EMF induced. Why EMF induced? Because this main flux. So this is cause, this is effect. Now, how this eddy current will oppose is simple. Observe here. Main flux is passing in the core. Now I am applying right hand thumb rule here. Main flux is in this direction. Main flux is flowing in this direction. Now, these eddy currents will produce a flux in opposite direction to main flux, like this. Like this. These eddy currents will produce, this is main flux and this is flux due to eddy current, will produce a flux opposite to main flux. Why? That is the cause. According to Lenz law, effect is opposing cause. Now, what is the direction of that eddy current? Generally, we are drawing eddy current like circulation somewhere, but actual direction of current, if it is required to draw, this is the exact procedure. Now, eddy current, flux due to eddy current is in this direction. Apply your right hand thumb rule there. In the direction of flux, eddy current flux, this blue line, thumb indicates that eddy current flux. Your curled fingers indicates the direction of current. Which current? Eddy current. So if I apply, I'm getting the direction of flux like current is like this. This is my eddy current direction. So eddy currents are circulating in the core in this way. See, my right hand thumb rule, thumb indicates flux direction, eddy current flux, flux due to eddy current, and that eddy current circulation is this forefinger. Okay, this is the path of eddy current. It will affect, definitely the eddy currents in the core will affect main flux. Due to that also slight reduction in main flux will be there, but that is we neglect because very small currents na they are. Generally we neglect, we don't consider this, but it will be there, effect will be there. If conductivity reduce, main flux will not affect that much, because why? If you reduce conductivity, which one will reduce? The current will reduce in that. What current? Eddy current. But flux is there, no? Flux is due to magnetic properties, not electrical properties. Conductivity is a electrical property, no? Okay. That's why small silicon we are adding. If you add more than this, the brittleness of the core will increase. The brittleness will increase. Means the magnetic property will disturb. Mainly brittleness increases means magnetic property, permeability of core. Actually, high permeability we are using, that permeability will reduce. Okay. Magnetic property should be as much as possible same, but slightly that electrical property of the core we are reducing by adding silicon. That is small 4 to 5%. Okay. So if it is required to show in any interview, we should draw this type of figure. What is the path of eddy current in the core? That depends on this eddy current flux. If you take main flux is in this direction, the flux due to eddy current is always opposite to that main flux. Accordingly, eddy currents will flow by applying right hand thumb rule here. This is itself eddy current. This is itself caused by main flux. This is itself caused by main flux. And how main flux direction we taken inside the core in the diagram? That depends on our winding, no? Primary winding, secondary winding, based on that main flux. And that flux is causing EMF. And that is causing some current. That current is eddy current. That is itself. Cause is input. Okay. So this is the way to reduce eddy current loss. One is by laminating the core and by adding silicon to the steel. Next, how to find this eddy current loss? Same, just like hysteresis loss mathematical equation, directly using that equation, we calculate eddy current loss. Right. The eddy current loss can be calculated. The eddy current loss can be calculated by using empirical equation. This is also by using equation W E equal to K Bm square F square T square into volume of core. Okay, K Bm square F square T square into V. So this is eddy current loss equation. These two equations you should remember. You should remember two equations, and the K here is a constant value, and the value of this is pi square by 6 sigma. Actually, these are all not required in any calculation. In even mains examination also, this constant K or in hysteresis loss we have eta coefficient. So these are all we never use. Just equation we are writing. That's it. Pi square by 6 sigma. Sigma is the conductivity of core, and this is flux density, maximum flux density it is, and this is supply frequency, and this is thickness of laminations. Thickness of laminations, because we are using laminated core, no? Thickness of laminations, and V is the same as hysteresis loss, volume. More volume, more eddy current loss. Less volume, less eddy current loss. Okay, volume of core. Both hysteresis loss, eddy current loss, both depends on same volume. If volume is more dipoles, so more hysteresis loss. So more volume is more, magnitude of eddy current will be more, so loss also more. So here important is, from this equation, the eddy current loss mainly proportional to square of thickness. What thickness? Thickness of lamination. If little thickness is reduced, now first generally tell me, which laminations will have more eddy current loss? Thick or thin? Thick lamination, thickness is more, eddy current loss also more. Thin lamination, Eddy current loss also less. If you reduce little thickness, so much eddy current loss will reduce because it is square of the thickness. Important, remember this is, if thickness is reduced by half, how much eddy current loss will reduce? 1/4, reduces to 1/4. Suppose if thickness is reduced to half from previous, whatever is there. Now what is the new eddy current loss? We proportional to T by 2 whole square, T square by 4, nothing but 1/4 times of previous. If 100 watts eddy current loss is there at a thickness of 0.1 mm, 0.1 mm or 0.5 mm, let us take, or let us take for simplicity 1 mm. If the thickness of that lamination steel plate is 1 mm, then eddy current loss is 100. Now the thickness reduces to half. What is the new eddy current loss? 1/4 times of previous. That is previously 100, now it is just 25 watts. If you reduce little thickness, eddy current loss reduces by so much. Okay. Now, just like hysteresis loss, here also two cases. First, observe the equation. Which are constants in this? K is a constant. It never changes. Thickness of lamination. Once you completed the construction, you cannot change the thickness, fixed. And then volume of core, fixed. The only variables are what? Bm and flux, frequency. Flux density and frequency. These two are the variables. Now again, we will get two cases, same as it is hysteresis plus. So write the two cases now. Case 1. Case 1. So eddy current loss equation is K Bm square F square T square. So actually volume no need to take because in both it is same, depends on volume. So we will neglect generally, that is V. Okay. Now case 1. If Bm equal to constant, when density is constant, if the voltage to frequency ratio is constant, then only it is V1 by F equal to constant. Now K already constant, volume already constant, T already constant. Now we have taken Bm also constant, assumption. Now what is the only variation? Frequency. Therefore eddy current loss proportional to frequency square. Now we are removing proportionality, so here I will take some other constant B. Previously I taken capital A, now I will take B here. B F square. This is eddy current loss in first case. Let equation 3 it is. Okay. Next, similarly case 2. Case 2. If Bm is not equal to constant, means the voltage to frequency ratio is not constant, then what is the relation? The Bm is not constant means what? Variable. So you have to take now two variables. Eddy current loss proportional to Bm square and F square. Both you have to take. And in that, what is the Bm means again? V1 by F proportional whole square into F square. Now this is F square gets cancelled. Finally V1 square. Therefore, the eddy current loss is dV1 square. Let it is equation 4. Okay. Now we have hysteresis loss in two cases, eddy current loss also in two cases. Now if you add both hysteresis and eddy current loss, you will get total iron loss. Okay. Before that, let's see some small numericals on eddy current loss also. Complete up to this. volume of core, total limbs and yoke, everything, because flux is going everywhere, no? If voltage increase, frequency decrease, hysteresis loss increase, you said that. But that depends on numerical, how much you increases. So only if you for theory question means not like exactly opposite means voltage increases you said and frequency decreases. How much you decrease voltage, how much voltage increases, how much frequency increase. If you know that percentage of voltage increase and frequency decrease, then you can say what happens to resultant hysteresis loss. But just if you say voltage increase, frequency decrease, you cannot say. Okay. Thickness, thickness is what? Thickness is lamination thickness, no? If thickness is changed, then volume will change. But anyhow, once construction of transformer is over, if there is a one transformer in front of you, can you change the thickness? We cannot change all this. What you can change? Only the supply side voltage or frequencies you can change. Okay. See question on this. Read the question. A transformer has eddy current loss of a transformer has eddy current loss of 100 watts at 200 volt 50 hertz supply. At 200 volt 50 hertz supply. Okay. What is the hysteresis eddy current loss? What is the eddy current loss at 160 volt 40 hertz supply? At 160 volt 40 hertz supply. Solve this. Simple. First write given at 200 volt 50 hertz supply. The eddy current loss 100 watts. Now we need to find what is the new eddy current loss at a supply voltage 160 and frequency 40 hertz. What is the new eddy current loss? So what you have to do? V by F unity check. Same or different? Same only, no? V1 by F 4. V1 by F 4. Voltage to frequency 4. Case 1 it is. Now in case 1, this is eddy current loss is proportional to frequency square. Now utilize this equation, this relation. Therefore, eddy current loss proportional to frequency square. Now write in two cases. WE2 by WE1 equal to F2 square by F1 square. WE2 is 100 into F2 means 40. This is F1 50. Initial frequency and after change the frequency. 40 square by 50 square. What is the answer? Yes, 64 watts, right. 64 watts. Okay, 64 watts. These questions are simple only if you remember two cases well. And there are some questions where you need to identify which case given first. That is important. Here directly you available voltage frequency, voltage frequency. But in some of the questions they will give it statement itself. Then you need to identify that is case 1 or case 2. Right, one more question. One more question. In the above question, in the above question, What is the eddy current loss? What is the eddy current loss at 200 volt 40 hertz supply? At 200 volt 40 hertz supply, what is the eddy current loss at 200 volt 40 hertz? Initially 200 volt 50 hertz. What is eddy current loss? 100 watts here. Now new voltage same, but only frequency reduced 40 hertz. What will be the eddy current loss? Which case it is first? Case 2. V by F is not same. 200 by 50 4, 200 by 40 5. Not same it is. Case 2 it is. So from case 2, what is the relation? Observe. WE proportional to V1 square. Eddy current loss proportional to V1 square. This is our case 2 equation. Now utilize this equation. WE proportional to V1 square. So what happens with respect to this? Voltage is same in both cases. 200, 200. If you substitute also, you will get the same value. The new eddy current loss also remains same 100 watts. Otherwise, substitute if you have doubt. WE2 by WE1, V12 square by V11 square. What is voltage in both cases? 200 only. 200 square by 200 square, 1. So WE2 equal to WE1. Both are same. So what it is? Same question, numerical, you may get theory question. How? In a transformer, by keeping voltage constant, supply frequency reduce. What is the eddy current loss? Increase, decrease, remain same, none of this. Answer is remain same. So this is same 100 watts only we get. Okay. So you may get theory question, you may get numerical question on these equations. Make a note again. Make a note. Just 2 points I will write again. Note. First point. In a transformer, by reducing both voltage and frequency, by reducing both voltage and frequency, such that V1 by F equal to constant. V1 by F equal to constant. Then eddy current loss is dash. What happens to this? If you reduce both voltage and frequency such that ratio is constant, then what is the eddy current loss? First question it is. What happens in the first question? Voltage reduced, frequency also reduced such that ratio is same. Then what is the new eddy current loss? We got 64, previously 100. So eddy current loss will reduce. Directly from equation you can analyze. So what is the equation? As it is case 1, eddy current loss proportional to frequency square. Now what is given in the question? Both reduced. Voltage reduced, frequency reduced. So as frequency is reducing, eddy current loss reduced. Or if they say in the same question, by increasing both voltage and frequency, such that V1 by F constant. Now what is eddy current loss? Increases, because now they are increasing now both. That's why. Okay. Next one more. By keeping voltage constant, if supply frequency increases, then what happens to eddy current loss? Voltage constant, supply frequency increase. Which case? Case 2. So case 2, what is the equation? Eddy current loss proportional to V1 square. By keeping voltage constant, frequency increase or frequency decrease, anything they given. If voltage is constant, frequency any variation. What is eddy current loss? Constant only. So it depends on mainly voltage magnitude, whether frequency changing or not, increasing, decreasing, anything they given. Answer is what? The eddy current loss remains same. Eddy current loss is remains same. Or they may give one more case. In a transformer, by keeping frequency constant, voltage increases. What is the eddy current loss? Increase. Why? Proportional to voltage square. Or by keeping frequency constant, voltage decreases. What is the new eddy current loss? Decreases. So all these points, no need to confuse. So forget everything. So we should not keep as much as possible many data in our mind, because it is not computer. Whenever it is saved and whenever it is required, it will come back. But this is very difficult, no? It won't come back. That is different. So forget everything. So whatever you learn, just learn simply, so that at any time it should come out. Okay. The subject is not difficult. The thing is only we make the subject difficult. So it is not difficult. So in total electrical engineering, machines itself the easiest and interesting subject also. But first we don't create interest there. That's why we don't get any interest to learn easily the subject. And whatever you learn in engineering, mostly you are in second years or third years or fourth years. So try to question yourself first. In your 4 years of engineering, what you learn in your 4 years of engineering, just after completion or in the fourth year, at least question yourself once. So finally, we are getting with a good aggregate, a good percentage, and we are coming outside with a good percentage. Certificate will be there, 90%, 80%, 85%, 70%. Okay, but what is the use? So outside, if you want to join or if you want to get any PSU or anywhere, good private sector also anywhere, competition will be there. So anywhere you have to you should show some subject there, that is in written test. Without that, just by observing, can they will give only in software industry it is there. Maybe in some software industry they will look for screening of the students, their percentage of marks. But this is all not possible in core side, technical side. So learn subject and try to crack as much as possible in the earliest any PSU, maybe state electricity or central or any private sector also we have in technical core side good jobs like Siemens. So good jobs are there in private sector also. Okay, good. So if you are learning, so don't waste your time at least from now, and as much as possible try to concentrate to go in the core side only. Maybe it will be little later, maybe 1 year or 2 years, 2 years or maximum 3 years. Definitely you will get somewhere, no doubt. But have with good content with you, good subject with you, particularly some subjects. Suppose in electrical engineering there are 10 subjects, you no need to be 100% perfect in all 10. At least 5 subjects, like main core subject: machines, power system, power electronics, measurements, control system, networks. So these are main important subjects. Anyhow, that analog part, digital, electronics part, signals and system. So most of the electrical students, they will neglect little. Okay, anyhow, if you neglect also, at least in the core subject, you should be very, very perfect if you want to join in any core side jobs, maybe state or PSUs, anywhere. Okay, but don't deviate in between. Some people will be there, they will try for 1 year, and there some 10 to 20% student will left, because once they did not get any good rank in GATE or ESC or any PSU examination, they will left the, they will move away from that sector and they will show interest in software side. Software side, if you struggle for 3 months or 6 months in good situation, not now, in normal good situation, definitely you will get. But is there any guarantee there? Entry is very easy there. However, it is very easy to entry, and exit also very easy. But in technical or code side, entry is little difficult. Exit is very difficult. You cannot come out. You can come outside, but wantedly they cannot remove you directly from the job. Okay, that security will be there. So try to choose a right path. If you want to get PSU, your rank should be below 300 as much as possible, because most of the students now preferring for PSUs first. So if it is below 300, no, mostly it is maximum 500 below. That's it. Marks we cannot say directly, because marks sometimes it will change. In 1 year, you may get the highest score is nearly 90 also. Or sometimes it is 80, 85 range also. So marks is changing, but rank wise I'm considering. For IIT, mostly you'll get up to 500. There is chance for getting good IIT. So recently, PSU, they are conducting own examination also. What is the problem? If you are perfect in GATE, you can crack anything, no doubt. If you are perfect in the GATE syllabus, you can crack any PSU examination very easily. The PSU, whatever they are separately conducting the examination, that is very easier than your GATE examination. Okay. Yes. Yes. GATE is necessary for some state electricity, like AP Genco also recently they released. But mostly people will not, maybe Genco only they release, but not other distribution transmission side, because if they release, it will be opposite to the government from job seekers. Mostly it won't happen completely. Maybe they released. Okay, no need to worry about that. PSUs, best PSUs like ONGC or HPCL, NTPC, Power Grid. These are all best. There are some small PSUs also. You will get, yes, Niti Bombay also good. Only the thing is, you are asking for preferring MTech, IITs or NSGs, MTech or job. So that is based on completely your economic status. So we cannot say MTech or jobs directly. So that is your economic status. If you are economically good in your family, then best to go MTech in IITs. For good rankers, I'm saying it is better to go MTech. Otherwise, if you are little economically down, then preferred PSUs there itself. Because anyhow, after completion of during MTech in any IITs, you may select definitely in any core, but waiting is important. No, there again 1 or 2 years you need to wait for that. Okay, that depends on your economical condition. Yes, MSQs are there, but uh, here this year newly they introduced this MSQ model. No? Multiple select question means in one question, uh, one option may be right, or two or may be right, or three may be right, or four may be right. Multiple select. But this year we don't get any question. Maybe by next year. So we need to check. We need to wait for the notification again from the other IIT. So there again they will mention the particular MSQs are there or not. We need to wait. IIT Bombay it is mentioned, but they did not given MSQs this year. Private companies, you need to fetch if you have any your seniors or your colleagues or your friends working in any private sector with a reference, they will take mostly. You need to fetch, you need to refer careers in all private sectors. Jail also good. So these are all PSUs. No need to say that this is best. But NTPC, I can prefer first preference. NTPC and Power Grid. These two are the complete our course set, and remaining HPCL. These are all also good one. But first I prefer NTPC, power generation there. Power generation side is you will have very good future. AEE or A. So anything first of all we need to get first, that is important. Anything is best. Yes, test you can take it anytime. If you missed by today and tomorrow or anytime you can take the test. Okay, so still so much time we have to search for which one is best. So we have completed hysteresis, eddy current separately. Now let's see total iron loss we need to write. Total iron loss. Individually we have seen now hysteresis, eddy current. Now write total iron loss. Iron loss. Wi. This iron loss is sum of two losses: hysteresis loss plus eddy current loss. Okay. Now two cases we have, case one, case two, and same two cases we apply for this also here. Case one. Case one. If Bm equal to constant case. If the V1 by F ratio is constant means flux density also constant. Then what is the iron loss? This is from equation 1 and equation 3. Hysteresis loss case 1, eddy current loss case 1. So add both here. That is equation 1, equation 3, both we are adding. That is Wi equal to AF is hysteresis loss plus BF square. This is the eddy current loss. Okay. This is iron loss equation in case 1. Next, similarly, case 2. If Bm is not constant, if Bm is not constant, this is from equation 2 and equation 4. Hysteresis loss case 2, eddy current loss case 2. Both I am adding now from equation 2, equation 4. If you add both, Wi total iron losses, what is the second equation? A V1 power 1.6 F power minus 0.6 plus eddy current losses B V1 square. This is total iron loss in case 2. Now, the important question here is maybe most of you who completed transformers in your engineering, those who are in third year, I think in second year it will complete. Maybe in two, maybe some of you may have transformers. Okay, anyhow, why the rating of transformer is in volt ampere? If anybody asks, what 90% people will tell? So everyone will tell mostly that. What is that? Why the rating of transformer is given in volt ampere or apparent power rating? Why it is? Because mainly we have two losses: iron, copper loss. Iron loss depends on voltage, copper loss depends on current. That's why volt ampere rating it is given. The rating of transformer is in volt ampere. Since mainly two losses in transformer, iron loss depends on voltage and copper loss depends on current. Okay, copper loss depends on current, accepted, because current passing through winding whenever changes, I square will change. So loss is variable. How iron loss depends on voltage? first, this question many times in some of PSUs and engineering services also asked. Iron loss depends on voltage. Now, first my question here, listen. First is, tell me, out of these two cases, in which case mostly the transformers are operating? Case 1 or case 2? Suppose in your house beside transformers are the distribution transformers. All the transformers, whatever is there in your street, they are operating in which case? Case 1 or case 2? Constant case or variable case? Okay. Okay, right. Okay, right. Most of you saying one and some of you saying second case. But answer here is first case. Mostly we operate transformers in first case only, because whatever the transformer is there in your street nearby to your home, what is the voltage supply coming to that always? Same or different? What is the voltage coming to your home first? Same, constant always. Means what is the input of transformer? That is also constant. Otherwise, if input of transformer is varying, your voltage also will vary, but that is not varying. And what is the frequency you are getting always? Always same 50 hertz we get almost. So V1 by F is constant or not? Yes. So always we operate transformers in case 1 only. Case 1 only we operate. Now, just now we are saying iron loss depends on voltage. Now, the question here in many PSUs and engineering services is, show how iron loss depends on voltage. Is there voltage in the equation first? Is there any voltage relation in this? No. Frequency only we have AF plus BF square. No voltage in this. Then how you are saying it depends on voltage? Yes, it depends on voltage only. Why voltage? Anyhow, frequency never changes. Input to output in transformers are everywhere. Our total power system dealing with 50 hertz only. Frequency never change. So you no need to talk about frequency. But the changes will be occurring voltages. Why? From one transformer to other transformer, slight voltage differences will be there. That is due to some number of turns or manufacturing defect, something. Some small voltage difference definitely will be there, but frequency almost constant. So this is the equation we are getting, AF plus VF square. When we are getting this, whenever V1 by F is constant, then only this equation we are getting. Okay. Now, whenever this voltage is variable, this equation will become second equation. No? Case 2, whenever V1 by F is not constant, suppose frequency same, constant, but little voltage you are reducing, supply voltage some little reduce, then this is case 2. In case 2, you will get this equation. Now, iron loss depends on what? Voltage only. Okay. So, iron loss depends on mainly voltage. Whenever voltage changes, definitely iron loss will change. Okay. So iron loss is a constant loss if the supply voltage is constant. So anyhow, we are getting constant voltage only. That's why we treat iron loss is constant always. Okay. Make a note here. Note. The iron loss of transformer. The iron loss of transformer is treated as constant. Is treated as constant if the supply voltage is constant. If the supply voltage is constant. If the supply voltage is constant. Suppose if voltage is variable, then definitely iron loss variable. And how it is variable, that is also we should know. How it will vary with voltage. Now, observe carefully, completed now up to this. Now, I will tell you in one topic in the Samperners test, why it is exactly in volt ampere rating, how we decide this is the capacity of transformer. Everything I will tell in Samperners test, not now. So in the particular topic, I will tell you how much rating, suppose 10 kVA transformer, how they will decide the rating, based on what they will decide, and why it is given in volt ampere. Okay, all I will give you in Sampner's test, not now. Observe. See, suppose if voltage is decreasing, frequency is constant. Which case it is? Case 2. Now in this case, what is the iron loss? Iron loss, second equation, it is A V1 power 1.6. Actually F power minus 0.6 is there. F power minus 0.6 plus B V1 square. But I will remove this frequency term. Why? Frequency constant we taken here. Observe. Voltage is reducing, frequency is constant. So as frequency constant, you can remove that particular term. Now what is that equation? Iron loss equal to A V1 power 1.6 plus B V1 square. So approximately Wi, approximately, this is also, can we take V1 square? Actually it is V1 power 1.6, but here V1 square we have. So in order to get V1 power 2, how much should be there? V1 power 0.4, 0.4. V1 power 0.4 means small value. So approximately, this is, I am considering like A V1 square, and this is B V1 square. B V1 square. So A, B are the constants, some value, some constant, that is some 0.2, 0.5 or 1, 2, something. So anyhow, iron loss is approximately proportional to square of supply voltage only. Approximately proportional to square of supply voltage. When it is, if frequency is constant and voltage is variable, maybe increasing or maybe decreasing, anything. This is approximately. Remember this condition we don't use in transformer, but you will use this statement again in induction motor. Same induction motor iron loss concept is same, 100% same concept there. Okay, induction motor you will utilize this iron loss proportional to voltage square. When case 2 it is, whenever voltage is changing, frequency is constant, approximately proportional to square of voltage. Remember, here you don't use induction motor only, you will use this. Okay, so iron loss varies with voltage. If voltage reduce, iron loss also reduce. If voltage increase, iron loss also increase. So if you want rated iron loss, then you must apply rated voltage to transformer. Okay, remember this point enough. So with this total iron loss we complete. Let's see some numericals based on this iron loss. See the question. See this. In a transformer, core loss is 100 watts at 40 hertz and 72 watts at 30 hertz. Then eddy current and hysteresis loss at 50 hertz respectively dash. So observe in this question, it is not given clearly, is it case 1 or case 2? Just given at 40 hertz at one frequency, the core loss, iron loss is 100 watts. Next, at 30 hertz, the core loss is iron loss or core loss, anything, 72 hertz. Now we need to find at 50 hertz. What we have to find? Eddy current, WE, and hysteresis loss. These two we need to calculate. Voltage is not given. And is it case 1 or case 2? That is also not given. Now, which condition you have to take? Case 1 or case 2? Which one we have to take? Case 1 we have to take. Case 1. Because voltage is unknown in this. If you take only it is case 1, then only you are able to solve. Otherwise, you cannot. Because in case 2, observe the iron loss equation. First equation, case 1. It is depends on only frequency. But in case 2, iron loss depends on voltage and also frequency, both are there. So whenever this is your, you need to identify which case we have to prefer, case 1 or case 2, based on the availability you need. So in the question it is not given clearly, that's why it is a case 1. So assume Bm equal to constant, flux density constant case. Then what is the constant case? Iron loss equation is what? In case 1, iron loss equal to AF plus BF square. This is, so we need to find eddy current and hysteresis loss. Tell me what is hysteresis loss equation at any frequency? AF only, no? AF means hysteresis loss and BF square means eddy current loss. So we need that AB values. Frequency they given 50, but AB unknown for us. How to find that AB? There are two conditions they given. So using the two conditions, find AB values first and then substitute in these equations. You will get WH, W. Okay. So first at 40 hertz, what is the iron loss given? 100. So iron loss is 100 equal to A into 40. Just apply in the equation. That's it. B into 40 square. Next, at 30 hertz, what is iron loss given? 72. This is at what frequency? 30. So A into 30 plus B into 30 square. Now there are two equations, AX plus BY equal to C. So use your calculators and put in the equation AX plus BY equal to C mode and try to solve this. You will get the values of A, B from here. Tell what is A value and what is B value. Calculate this. So do the calculations simultaneously. Don't take directly. Tell AB values. What is A value? A is 2.1, B is 0.01, right? A is 2.1, B is 0.01. Okay, check all of you, same. Now, once you know A, B, now you can find hysteresis and eddy current loss at any frequency because hysteresis loss is AF, eddy current loss is BF square. Now you can find anywhere. So we need to find it 50 hertz. So B value is 0.01 into 50 square. This is how much? 25. And WH is AF. A value is 2.1. 2.1 into 50. This is 105 watts. Eddy current is 25. Hysteresis loss is 105. So sequence should be the same only. 25, 105. So only one option is there. Option A is correct. Yes, right. Okay, next question. Completed. Next. The two equations you have to solve using your calculators. Put your calculator in equation mode, AX plus BY equal to C. So AB are the unknowns here. That AB calculated. Next. Read the question. A 200 volt 60 hertz single phase transformer has 200 volt 60 hertz has hysteresis loss 250, eddy current loss 90 watts respectively. Okay. If the transformer is now energized, now new voltage given 230 volt and frequency given 50 hertz. What is the core loss? Iron loss is. So sum of these two is total iron loss. Wi1 is total how much? 250 plus 90, 340 watts. Now what is the new iron loss? That is the question. So try to guess. Which case it is first? You need to check. Case 1 or case 2? Check it is 200 by 60, 230 by 50. Same or different? 200 by 60, 3.33, and 230 by 50, 4.6. So both are different. So case 2 it is. Okay. Yes, case 2. Now in case 2, don't use iron loss equation directly. You don't get any answer. If you use as it is case 2, what is the iron loss equation in case 2? A V1 power 1.6 F power minus 0.6 plus B V1 square. If we use this equation, voltage is frequency there. Voltage is 230, frequency 50. That is okay. But where is the AB values? Do you have AB values here? No. So AB unknown. So directly don't use this equation. You don't get if we use this equation directly. Then what is the procedure? Simple. We have WH1, WE1. Calculate what is WH2 and what is WE2 separately, individually. Calculate individually hysteresis loss, individually eddy current loss. Then add these two, you will get the total iron loss. Case 2, hysteresis loss separately, eddy current loss separately. Because AB unknown, then you have to proceed individual calculation. Then add both. Okay. So case 2. In case 2, what is hysteresis loss? WH proportional to V1 power 1.6, F power minus 0.6. And eddy current loss is proportional to V1 square. So use individual calculation. Now write it is in two cases. WH2 by WH1 equal to V12 by V11 whole power 1.6 F2 by F1 whole power minus 0.6. Okay. Minus 0.6. Substitute the values. We need WH2. WH1 we have. How much that is? 250. Substitute carefully. 250 into V12 means new voltage. What is the new voltage? This is V12. This is V11. F1, F2. Substitute all the values. V12. So I'm substituting here. WH2 equal to 250 into new voltage 230 by 200 whole power 1.6 into F2 means 50. F1 is 60 whole power minus 0.6. So take care of calculation. If you miss any small numerical minus plus also, it will change. Calculate what is WH2. In the same way, WE2 by WE1 equal to V12 square by V11 square. Now, WE2 equal to WE1 is there 90 watts 230 square by 200 square. So calculate these two values. What is WH2? Tell me. 179. What is WH2? 348. Okay. WH2 is 348. And what is WE2? WE2 is 119. 119. And sum of these two is total iron loss, Wi2. We need to find total core loss here. So Wi2 equal to 348 plus 119. So this is 467. Right. Yes. 467 watts. This is the total iron loss. Now clear. If we use directly the second equation, you cannot find the calculate individually hysteresis, eddy current, and then add both. You will get total iron loss. Okay. Next question. Completed all of you? Next question. See this question. In a transformer, the total iron losses are equally divided at rated voltage and frequency. If the transformer is operated at same frequency but at 90% rated voltage, the percentage reduction in iron loss when compared to rated iron loss. So first of all, in this question, the data is not visible properly, but you should understand accordingly. You have to assume some data, then you need to solve this. So here there is no voltages, no frequency, and there is no initial iron loss. But now you need to still identify percentage reduction in iron loss. See, in a transformer, the total iron losses are equally divided at rated voltage and frequency. What is rated voltage and frequency? Not given. So you assume the rated voltage is V1 and frequency is F. So at this rated voltage and frequency, the total iron losses are equally divided. Means total iron loss is what? Sum of two losses, hysteresis, eddy current. So among the two, this is equally divided. So you assume some data. So let us take the iron loss is 100 watts or 1 watt or 10 watts, anything you can assume. So for simplicity, I'm taking 100 watts. Now this iron loss is equally divided between given between what it will divide between two losses, hysteresis, eddy current. So in this, WH1 is 50 watts and WE1 is 50 watts. Okay, WH1 50, WE1 also 50, equally divided. That's why we take it. Now question is, if the transformer is operated at same frequency, so frequency now same, but what is the change? But at 90% rated voltage. Previously V1, now 90% rated voltage means 0.9 V1. Previously we assumed V1, now 90% of that 0.9 V1. So at this voltage and frequency, first you need to find what is total iron loss. Okay, then if you check these two values, then you will come to know how much is reduced, percentage reduction. We need to find percentage reduction in iron loss when compared to rated iron loss, means 100 watts. So first find individually hysteresis loss and eddy current loss, then add both, you will get total iron loss, same as it is previous question. Now here this is V11, this is V12. What is the case? It is case 1 or case 2? Case 2 it is. See, ratio V1 by F, but here 0.9 V1 by F. Both are not same, different. Case 2 it is. So using case 2, WH proportional to V1 power 1.6, F power minus 0.6, and WE proportional to V1 square. So calculate individually, same as it is previous question. Every data is available now. WH2 by WH1, V12 by V11 whole power 1.6, F2 by F1 whole power minus 0.6. Okay. Now WH2 we need to calculate. WH1 we have 50. V12 is 0.9 V1 divided by V1 whole power 1.6 into F2. F2 means F2 and Fn both are same frequency, no both. So directly 1 power 0 minus 0.6. So calculate WH2 from this. So in the same way, calculate WE2 also. WE2 by WE1 equal to V12 square by V11 square. So WE2 equal to WE1 we have 50. V12 means 0.9 square. Directly I'm writing 0.9 square. Calculate this. WH2 how much? WH2. So WIV square is approximately, no, that is here in transformer we never use that relation that I said. In induction motor you will get that. So you should not get doubt why it is taken as V square. That is approximation. WI proportional to V square approximately. But exact calculation we should not use that V square. Yes, WH2 how much? 84, 42.24. Okay. WH2 is 42.24. And what is WE2? WE2. 40.5. Okay. WE2 is 40.5. Okay. Yes. What is the total iron loss now? Total iron loss. Sum of these two. Just add these two losses. 42.24 hysteresis loss plus 40.5 eddy current loss. So this is how much? 82.7 percentage, approximately 82.7. 82.7 watts. This is in watts. 82.7 watts. Previously, what is the iron loss? Initially, we taken 100. Now, how much new iron loss we got? 82.7. How much is reduced? 17.3%. 17.3 watts reduced. So in percentage also same you will get, because 100. That's why taken. That's why taken 100 directly. So whatever it is reduced, therefore iron loss is reduced by 17.3 percentage. Okay, option B. Yes, right. Check all of your numerical. Those who are getting little variation, check. This is right on. Yes, you take 200 also, no problem. Take any value, or you don't take any value, just assume WI1 equal to W. Anything you can take. Take WI1 equal to W. Just W, some watts. Or take one. Take 1 watt. Okay, anything you can take. So for simplicity, I taken 100 so that directly we can get percentage. Now here, whatever is reduced, that much percentage directly. 17.3 percentage. Next question. So this is gate 14 question. In gate 21 also same as it is model. Whatever we got gate 14, no? Same model in gate 21 for 2 marks. See, question is very big, but if you read with patience, nothing is there in the question. Don't fear of size of questions. Read the question. Okay, I will give break after this question. We take break. So read the question. The core loss of a single phase 230 by 115 volt 50 hertz power transformer is measured from 230 volt side by feeding primary from a variable voltage, variable frequency. Variable voltage, variable frequency. Means what? From this variable voltage and variable frequency, any voltage, any frequency you can apply. Voltage reduce, frequency, both you can reduce. Actually, whatever the source available, no? What is the input of transformer? Generator. So in normal generators, you cannot change frequency directly. Suppose there is an alternator. Alternator is given to the transformer as input source. There, frequency we are generating constant 50 hertz. Voltage you can change by excitation. That's it. Voltage variation is there, but frequency is not there. But nowadays, due to the power electronic drives, we can control voltages, frequency like anything. So using this power semiconductor devices, you can change now. So this source is given. So anyhow, so these are all not required for us. Simply you read from here enough. This data is enough for you to solve this question. Read from here. The core loss is 1050 for 230 volt 50 hertz. Core loss means iron loss. The iron loss is 1050. At what voltage and frequency? At 230 volt 50 hertz. Okay. Next, the core loss is again measured to be 500. Let WI2, second case. How much? 500 watts. At voltage is 138 and frequency 30 hertz. The hysteresis and eddy current loss of transformer for 230 volt 50 hertz. We need to calculate what is hysteresis loss, what is eddy current loss. At what frequency? 230 volt 50 hertz. Now first check here. At 230 volt 50 hertz, already they given iron loss is how much? 1050. Same they are asking again. So iron loss is sum of two losses, no? So 1050 total iron loss. In that, how much hysteresis, how much eddy current? The question. So if you observe, sum of the two must be 1050. And if you add all the four options, they given same like that only. Sum you will get 1050 only in all options. So definitely we have to solve. Otherwise, by observing some option, suppose if two options are 1050, if there is no time to solve, at least by chance we can get, we can put any one, but all options is having 1050, we should solve. How to solve? What is WH equation? Which case it is? That is important. Which case it is? Tell me. Case 230 by 50. 138 by 30. Same or not? Yes, same it is. Check it is which case? Case 1 or case 2? Case 1 it is. What is the value we get? 4.6. 230 by 50. V1 by F. 138 by 30. Same you will get. So case 1. So in case 1, what is hysteresis loss equation? WH equal to AF. And what is eddy current loss equation? BF square. So that A, B value is required for us. For that they given two cases. 1, 2. So utilize same as one question we solved previously. Find AB values. So V1 by F equal to constant. Then what is the iron loss equation? Total iron equation is AF plus BF square. So utilize this equation. At 50 hertz, 1050. At 30 hertz, 500. Substitute that. First, at 50 hertz, iron loss is given. What is that iron loss? 1050. AF, A into 50 plus BF square. B into 50 square. Next, at 30 hertz, one more case is given. Iron loss is how much? 500 watts. A into 30, same equation, plus B into 30 square. So solve these two equations. Solving AX plus BY equal to C formula. Solve, tell what is A value and what is B value. Bhargav, in the previous question, you are asking WI1 is what you are taking WI1? WI1 is not mentioned. You can take any value, you can take. How to find percentage? You should know that one first. Percentage calculation. Percentage reduction. High value minus low value by high value. So this is high value, no? WI1 is the high value, WI2 is the low value. Now what is the percentage reduction? How to find percentage reduction? Same, anything you take, you will get the same answer. High value minus low value divided by high value into 100 will give percentage reduction. Okay, now you try this, you will get. What is A value? Okay, good. Yes. A is 10.16. B is 0.216. Yes. Once you know AB, now it is very simple. Therefore, at 230 volt, 50 hertz, we need to find hysteresis loss and eddy current. Hysteresis loss is AF, eddy current loss is BF square. 10.16 into 50 and B 0.216 into 50 square. What is the answer? 10.16 into 50 is 508 and this is 442. 542. Yes, sum of these two should be 1050. 542 watts. Okay, option A will satisfy. Hysteresis loss and eddy current loss. Okay, got it all of you this? AB calculation you should know. Calculations you should know how to do this in calculators. Completed? So this question is in gate 14. Now see in gate 21 almost same question. Gate 21 it is 2 marks. Same model, same model. You try this question and take break. After break, we will see the answer of this. Okay, take break. Same as previous question. GATE exam virtual calculators we have. GATE examination, we have virtual calculators. So you also try to practice in the same calculator. Okay, so take break for 15 minutes. So got it all of you same? Yes. Same as it is previous question. It is initially total iron loss is 2500 watts. This is at a voltage of 440 volt, frequency 50 hertz. Now again there is a total iron loss of 850 watts. This is at a voltage 220 and frequency 25. So both reduced to half. Voltage reduced to half, frequency also reduced to half. Means V1 by F same or not? Yes, same. So case 1 it is. So we need to calculate at nominal voltage and frequency. So which one they referred here as nominal voltage? This one, nominal voltage and frequency. So we need to find at 440 volt 50 hertz. At 440 volt 50 hertz. What is the hysteresis loss and what is the eddy current loss? And what should be the sum of these two? Whatever is there here, 2500. So if you observe now in the option, only two options we have, 2500. Remaining, that is option A, option B. And remaining C, D is, what is the sum? 600 plus 250, 850. So that is not correct. Out of A and B, answer will be there. So same as the previous question, as it is case 1, what is the iron loss equation? AF plus BF square. Now use this here, 2500 equal to A into 50 plus B into 50 square. Next from here, 850 equal to A into 25 hertz plus B into 25 square. Calculate AB values again. A value and B value. What is A? In virtual calculators, if you are not able to solve one by one, multiplying first equation with 25 and second equation with 50. You should be aware of this calculation. Even without calculator, without calculating actual virtual calculator also, you can solve. 1 minus 2, equation 1 minus equation 2. So you do that, you will get. What is the A value? A is 18, B is 0.64. Okay. Now with this WH AF, okay, WH 18 into 50, 900 watts, and WE is BF square, 0.64 into 50 square, so you'll get 1600 watts. Okay, WH W directly from option A. Hysteresis and eddy current loss, same as it is previous question. Going to next question. Next, see, this is also one of the gate question. For a single phase 2 winding transformer, the supply frequency and voltage are both increased by 10%. The percentage changes in hysteresis loss and eddy current loss respectively. Which case it is? Suppose there is some voltage and frequency initially. Now what happens here? The supply frequency and voltage both increased by how much? So this ratio is V1 by F. So new voltage is how much? 10% increase. New frequency how much? 10% increase. So whenever both voltage and frequency simultaneously 10% increases, what is the V1 by F ratio? Constant only, no? voltage increase, frequency also increase. How? Same 10% increase. So V1 by F is constant. Now in constant case, we have hysteresis loss proportional to frequency, eddy current proportional to frequency square. Now how much frequency increases? 10% increases. So whenever frequency increased by 10 percentage, how much hysteresis loss? Directly 10 percentage. Increased 10% increase means plus 10. And eddy current loss how much increases? Frequency square it is. Initially F. Now 10% frequency increase means what is the new frequency? 1.1 F whole square. So WE proportional to 1.1 F. Why 1.1? 10% increases. So if you solve 1.21 F square we get. So previously 1 into F square. Now new eddy current loss is 1.21 times of F square. Means how much eddy current loss increases? 21 percentage increases. Hysteresis loss 10%, eddy current loss 21%. Option A is correct. Okay. Next question. Here minus 10 indicates decrease. So plus both are plus only because both increases. Hysteresis loss increase, eddy current loss also increase. See, eddy current loss proportional to frequency square initially. Now 10% frequency increase. What is the new frequency? Initially F. Assume that initial frequency F. 10% frequency increase means what is the new value? 1.1 F only, no? So that is I substituted and whole square it is. So 1.21 F square. Then 21 now 1.21. Initially 1 only, now 1.21. So total 21 percentage increases. Okay. Now the hysteresis loss, eddy current loss. It is every time we cannot say which is greater here. So sometimes you may get eddy current loss is less than hysteresis loss. So every time we cannot say that is. Okay, you need to solve. How is eddy current 21? See, Emma actually previous WE1 proportional to F square. Okay, rated frequency that is. What is new frequency? WE2. That is new frequency is what? After 10% increase. What is the new frequency? 1.1 F only. No? Assume that 50 hertz. What is 10% of 5? 0.5. Okay, so 50.5 whole square or 1.1. So I'm taking directly 1F. Now 1.1 F whole square. Now what is the new value we'll get here? 1.21 F square. Now compare WE2 and WE1. Here F square only. But now 1.21 means how much value increase? 0.21 increases. No, that is 21 percentage. Directly I take it. Okay. Divya also correct. Still some of you not understanding why 1.1. What is the 10% of, suppose 1 is the initial value 1. What is 10% of that one? 0.1 only, no? Already 1 is there. Now 10% of that value increase. What is 10% of 1 is? 10% of 1, how much? 0.1. Then that is added to previous term. That is already 1 is there. Now additional 10%. What is the new value? 1.1. So 1.1f whole square, because it is square of that frequency. So 1.21. Now clear? Vinita, I said iron loss is constant. When iron loss is constant, if voltage is constant. So when voltage changing, then iron loss will change. But practically, whatever the transformers we are operating, is we are voltage changes? No, we are not changing any voltage. But here in the questions, numericals, many variations we are doing. No, we are changing voltages, reducing, increasing, anything. So whenever voltage change, definitely iron loss will change. But if voltage constant, iron loss constant. But practically, whatever we are operating, they are all constant voltage. That's why iron loss is constant. Okay. Yes, right. Yes. 10% decreases means then 0.9. Yes, right. No, not -10, -21. See, in the same question, if they given voltage and frequency both reduced by 10 percentage, what is the answer? See, in the same question, if voltage and frequency both reduced by 10 percentage, 10 percentage. Okay. Anyhow, V1 by F ratio constant. So what is the formula? WH proportional to F and WE proportional to F square. Now what happens? Frequency reduced by 10 percentage. So hysteresis loss also reduced by same, because this is directly proportional. But eddy current loss is what? Square of frequency. So initially F, now 10% reduce. Now what is the new frequency? 10% reduces. Initially 1, 10% reduce means what is the new value now? 0.9. So 0.9 F whole square. What is this value? 0.81 F square. So initially in WE1 here, F square is there. Now how much is there? 0.81 F square is there. Means some value reduced or not. Previously 1 F square, now 0.81. How much reduces? 0.19 reduce. Means percentage is 19% eddy current loss reduce. Not 21 now. Whenever 10% increase, then it is 21% increase. If 10% increase, 10% decrease. The percentage overall you don't get same. So 19% now it is decrease. Now clear? Yes, just like aptitude question, 10% increase, 10% decrease. Next question. See this question. So same question on iron loss with a little small variation they given like. So first read the question. A single phase 400 volt 50 hertz transformer has iron loss of 5000 watts. Initially iron loss is 5000. This is at what voltage? At 400 volt 50 hertz. Okay. Now same transformer again operated at 200 volt 25. Then the iron loss is almost same model will be there, 2000. and this is at 200 volt, 25 hertz. So both half reduced. When operated at when operated at 416 volt, 52 hertz. The question here is the hysteresis loss divided by eddy current loss. So little small variation they given. Just that's it. Same model. Find hysteresis loss, eddy current loss at this voltage and frequency. Now take the ratio of that. That is they are asking. Now which case it is also? Case 1 only, no? 400 by 58. 200 by 25, 8 only. 416 by 52, 8 only. Okay, this is case 1 it is. So as it is in case 1, again calculate A, B values using two equations. Initially 5000 at 50, A into 50 plus B into 50 square. Next 2000 watts, this is at 25 hertz. A into 25 plus B into 25 square. AF plus BF square I applied and find AB values from this. A value how much? B value how much? And once you know AB, at this voltage and frequency, find what is WH. Same formula AF and WE, BF square. Find AB values first, then WH, W. What is A value? You cannot say WH greater than WE always. It depends on the values only. A value 1.44. A and B. A is 60, B is 0.8. Is it right? AB? Okay, right. Next, AF 60 into, we need to find at 52. And B is 0.8 into 52 square. Calculate hysteresis loss. What is hysteresis loss? Three one two zero, and eddy current loss is 2163. And take the ratio of these two. WH by WE directly. Ratio is how much? Ratio WH by WE. Hysteresis loss divided by eddy current loss is required. 1.44, right? 1.44. So this is the answer. So same model, but they ask little different ratio. They are asking hysteresis loss by eddy current loss. Yes. Okay, enough. Okay, next. See this question. Last question. In a power transformer, the core loss is 50 watts at 40 hertz and 100 watts at 60 hertz under the condition of same maximum flux density. So directly they given maximum flux density is same or constant it is. First case it is directly they given the core loss at 50 hertz will be dash. So given that at 40 hertz, the iron loss or core loss is 50 watts. Again at 60 hertz, the iron loss is 100 watts. This is at same flux density, means constant case 1. Now we need to find the iron loss at where 50 hertz case. So in order to find iron loss at 50 hertz, what is the formula in case 1 for iron loss? AF plus BF square. So we need to find that AB values. That AB we can find from these two equations. Equation 1, equation 2. Apply this. So first 40 hertz. At 40 hertz, what is the formula? AF plus BF square. Same I am applying. 50 equal to A into 40 plus B into 40 square. And at 60 hertz, iron losses 100 equal to A into 60 plus B into 60 square. Calculate AB values and then substitute here A into 50 plus B into 50 square. Calculate, you will get the answer. The final answer is how much? Iron loss at 50 hertz. Iron loss at 50 hertz is how much? Yes, you can find. Once you know AB values, you can find iron loss at any voltage and frequency. Same thing, Vishnu, same thing. So we have to respond to them, no? What we can do. Yes. What is iron loss? Final tell me. Iron loss is 73 watts, right? Finally, iron loss at 50 hertz. AB you calculate whatever it is. Final answer I'm writing 73 watts. Okay, check it is. So still iron loss problems are not completed. Still with respect to OC test. So once we complete OC test, we'll see one numerical based on that how we are calculating again iron loss from open circuit test, because OC test we conduct mainly on transformer to find iron loss only. Okay, how we will see that next step. So with these two major losses we have seen up to now. Two major losses. First is copper loss and second is iron loss. So one is variable, one is constant loss. Copper loss depends on current, so whenever current change, loss will change. Iron loss depends on voltage. If voltage constant, iron loss constant. So generally that is only the we are applying now. That's why constant loss we treat. But when you change voltage, iron loss will change definitely. Okay. Now let's see the minor losses briefly once. What are the minor losses we have? Two minor losses we have. One is stray load loss and dielectric loss. See, the third loss. This is minor loss, stray load loss. Stray load loss. Other than this transformer core and copper winding, other than this, so there are some other parts in transformer or not? What are that? Like if you observe, complete core and winding we have in the tank of transformer tank, and in the tank you have some additional bolts and you have some bushings. In the bushing, the at the center we have one metal pin to take that copper wire outside from the inside winding. There is some metal pins. In that also some losses will take place. So these are all comes under stray losses. So mainly stray load loss, again we divide into two parts. One is copper stray load loss. Copper stray load loss. And second is iron stray load loss. Iron stray load loss. Copper stray load loss and iron stray load loss. So what is this copper stray load loss? It is takes place in copper windings. So already we have seen there is some I square R loss in copper winding, but this is an additional I square R loss in copper winding. But when and how it will takes place is observed. So previously, if you remember, we have seen uh, in the transformer winding topic, starting construction transformer winding, it is made up of copper. And what type of conductor we are using? So there I given some different types: solid, stranded, composite, stranded, and bundle. So there I said solid conductor is having disadvantage of mechanical strength mainly. Mechanically strong, that is. So we cannot make a coil easily by hand. So winding is difficult with that. So due to that we are not using. And one more problem of that solid conductor is this copper stray load loss. What it is, observe now. Observe here. If we use a solid conductor, not thin wire, if we use a solid conductor, whenever alternating current is passing through this, there is a skin effect. One problem that is over, already we have seen. And other problem I am showing here, observe. See, current is passing through this. Through any current carrying conductor, there is a flux around that or not? Yes, there is a flux around the conductor. By right hand thumb rule, you can find direction of flux. If current is flowing in this direction, your four fingers, however they are curling, in the same direction, flux also rotating around that. Now this is our alternating current. Now around this current, a flux is rotating. So I am applying right hand thumb rule. This is the flux direction I am getting. Flux around the conductor. Okay, current direction is thumb, four fingers is flux. Now this flux is alternating only, no? Where is this winding we are placing? Winding we are placing on core, stationary, that is. Anyhow, winding stationary, but as flux is time variable flux, it will cause an additional EMF in the conductor. An additional EMF in the conductor. Due to this flux, due to that EMF induced, very small, as it is solid conductor, more cross section is available. Now, solid means what? Thickness is more, then more cross section available. Then in this small cross section, a small currents will circulate. A small currents will circulate here. Small currents throughout the conductor will circulate due to this flux around the conductor. Now these currents we call stray currents. See, already main current is there. What is that? I1, I2, primary current, secondary current. That is over already. Don't confuse that. These currents are additional circulating currents in each conductor or copper wire. So this is called stray current, circulating current or stray current. Now due to that, a small I square R loss additionally takes place. This is called copper stray load loss. So what is copper stray load loss? It is an I square R loss additionally taking place in the conductor due to circulating currents or stray currents. Now, how to reduce these stray currents or copper stray load loss? How to reduce? This loss is variable or constant? Tell me first. Variable. However, copper loss I1 square R1, I2 square R2 is variable. This is also variable because if magnitude of current is changing, magnitude of flux will change. If flux is changing around that circulating current magnitude again change, then loss also change. So this is a variable loss. Now, how to minimize this loss? How can we reduce? Because of this reason, we are not going to solid conductor. We are going to stranded conductor. This one, thin wires. We don't take single solid wire. We take small thin wires, many wires. This is called stranded conductor. Now, what is the advantage with stranded conductor? If current is flowing through this, what is the cross section area available to circulate current? Very, very small, thin wire, no, it is. So then magnitude of stray current reduce, loss also reduce. So this is other reason why we use stranded conductors in windings mostly. Solid conductor is provided. Okay. So write one point if you want here. Copper stray load loss. It is an additional I square R loss taking place. It is an additional. It is an additional I square R loss taking place in solid conductor. An additional I square R loss taking place in solid conductor due to stray currents. Due to stray currents. Due to stray currents. It can be reduced. It can be reduced. It can be reduced by using stranded conductor in place of solid conductor. It can be reduced by using stranded conductor in place of solid conductor. Due to skin effect, current is there on surface. Anyhow, current is flowing through conductor. Around that there is a flux or not? Yes. That flux will link with the same conductor. That flux link with same conductor. Now it will cause some small EMF in the turnout. Yes. Due to that, as surface area is more for solid, current will circulate there. That is called stray current here. So to reduce that, anyhow, we are using stranded conductor. This problem will not come. This is for only solid conductor, copper stray load loss. Otherwise, if it is stranded conductor, almost it is negligible. There is no stray currents. Okay. So this loss is variable, which depends on load of transformer. This is a variable loss. Now, second, iron stray load loss. Observe what it is. Iron stray load loss. Observe. So where the complete setup of this transformer we are placing. So we are placing the complete transformer in a tank only. No? This is our transformer core. Okay. Transformer windings. This is our transformer tank. This is what? Tank of transformer. Transformer core, transformer winding completely immersed in the tank, which is filled with the transformer oil completely. Okay. Now let it is secondary side load is connected and primary side source is connected. Now we know very well, whenever there is a load on transformer, currents magnitude in the windings are high, I1, I2. Now there is a leakage flux on primary and also there is a leakage flux on secondary. So there is a small amount of flux leakage. A small amount of flux is leakage. Now, there is a chance that whenever load magnitude is very high, under heavy load condition, there is a chance that a small amount of leakage flux may touch with the tank. A small amount of leakage flux may touch with the tank. It may touch sometime. Suppose if load is very high, current is very high, flux produced is very high, leakage flux also variable. So already we know what is the leakage flux, variable flux or constant flux, variable. And what is the main flux of transformer in the core? The flux in core, constant or variable? Constant. Constant flux device it is. But leakage flux is not constant, variable. If load changes, leakage also changes. Now leakage flux depends on what? Load. Then where main flux depends? Important question. Main flux depends on what? Main flux depends on supply voltage and frequency. The main flux depends on source, but leakage flux depends on load. If load is changing, leakage also will change. Now under heavy load condition, leakage is more. Then some flux may touch with tank or not. Yes. Now it will cause some EMF in the tank body or not. Yes, because tank is made up of what? Iron. Now this is having some conductivity or not? Yes. This is not insulator, no. This is a like some conductivity is there. Now due to that, whenever flux links with any conductor, some EMF induced, and there will be a small circulating currents throughout the tank. A small circulating currents will pass. So this is only whenever we touch some of the transformer. Generally we don't touch now in the streets. Will you touch while going the transformer tanks? No, we never touch. But actually when we touch transformer body in the labs with small voltage, if you check, little shock type feeling you will get. Like if you touch your PC CPU also, sometimes CPU body, you will get some shocks. That is not actually direct main current shock. That is due to some small circulating current only inside the iron body. Okay, on the body small currents will circulate. So when you touch this, you will get shock, but not very high, very small only. That is because magnitude of current is very small here. Actually the oil is acting as insulator between the core and tank outside, so very less chance to get this. But still whenever leakage flux link with the tank, it will cause some iron I square R loss. Just like eddy current loss in core, it is also some loss. This is called iron stray load loss. Okay, this is the current in tank IT and resistance of tank RT, then I square R loss in tank. So that is called iron stray load loss. So what is iron stray load loss? It is an I square R loss taking place in the transformer tank, due to whenever leakage flux links with the tank, whenever leakage flux links or connect with the tanks. Now this loss is variable or constant? Iron stray load loss is variable or constant? Not constant. So generally people will think iron is constant loss always. Core loss of transformer constant, but iron stray load loss is variable. Why? It depends on what? Leakage flux, and leakage flux is variable. And where it depends? It depends on load on transformer. If load is changing, definitely this loss will change. Okay, now the question is how to reduce this loss. How can we reduce? How can we reduce this loss? Hmm. How can we reduce? Yes, earthing, one method. Good. Okay. Okay, good. So thinking little, right? All of you, right? So you are saying increase the size of the tank, and some of you saying by earthing the tank. Okay, we can reduce like that, but whatever you are saying, size increasing, because if you increase if you increase the distance between core and tank, distance, this is transformer core and tank, right? It is. If you increase this distance, definitely leakage flux will never touch the tank, because leakage flux cannot travel so much distance. It cannot travel little, it can come out, but not very high distance. So like that, you can reduce the leakage flux. That is Iron-Stay-Load loss. But practically, we don't prefer this. Practically, we don't prefer. Okay, your idea is good. If you increase the distance or size of the tank, loss will reduce. But here, before doing this, you should think one more is you are getting loss. Okay, you have some solution for this. At the same time, whatever the solution you found out just now, there is a drawback with that. What is the drawback? When you increase the size of the tank, then it need more oil in the tank or not. Little size with distance increase, so much oil you need to fill there. Then what is the cost of that oil additionally you are placing, or what is the maintenance of that again, and what is the weight of the transformer totally? Size increase, cost increase, weight increase, maintenance increase, and how much loss you got previously. First, you got a loss of some 1 rupee, but you are spending on the 10 rupees. Is it preferred? No. Because of this reason, whatever that loss we are getting, and that loss also not continuously in a day. Suppose when there is load, heavy load, at that duration only this loss. Under normal condition, you don't get this loss also. So generally we neglect this. We don't consider, we neglect, because already it is a very very small amount. Then why should we spend so much on this? Due to this reason, generally we neglect this, and this is also one of the loss. Okay, this is also one of the loss. Some of you may get one more. Yes. Eliminating leakage flux. We are eliminating leakage flux. Eliminating means we are reducing. You cannot eliminate in transformers. You cannot eliminate. Now, what are the methods to reduce leakage flux? We are using concentric interleave winding for core type, and we are using sandwich type winding for shell type, as much as possible to reduce leakage flux. But you cannot eliminate completely. Okay. And some of you may also getting doubt. We are using tank is iron. Let's use the tank with wood. Can we design the tank with wood? Is it preferred? Have you seen anywhere transformer made up of wood outside tank? No. We cannot use wood now, because it is not uh, reliable. Particularly means if we use wooden tank, oil is there inside, so there is a problem of leaking, or sometimes turn to turn short circuits may take place inside the transformer, so there is a chance of burning or fire. So wood is not at all suitable, so we never prefer. Tank is made up of iron only or steel only, so there is some small Iron-Stay load loss, negligible it is. Okay, this is about stray load loss. This is variable loss. Iron-Stay load loss is variable, remember that point. Next, last one in the losses is what? Dielectric loss. Dielectric loss. Where this loss will take place? This loss takes place in insulating materials. Dielectric related to insulating materials. Dielectric loss taking place in insulating material. Tell me where we have insulating material in transformer. Yes, immediately you will tell now oil. Yes, transformer oil acting as insulation, insulating medium, but that is not original insulating material here. Where we use insulating material, if you remember, in the transformer winding placement. If you remember how we place, if it is the core, are you placing directly winding on core? No. First, what we placed? Some insulating material like impregnated papers we placed. Some number of papers with some thickness, depends on some voltage rating, that is, and then LV winding first, and again insulating material we placed, and then again HV winding we placed. So this type of procedure we followed. No, so there we have major insulating material. Oil is insulating material, okay, but that is having, compared to this insulating type of material, that is very less dielectric strength. But this material between winding to winding or core and winding, this dielectric strength is very high. So this is we are considering mainly. Observe what happened. So I am taking some part in that, that is let it is HV winding. HV winding outside, HV winding, and then we placed in between insulating material is there, between LV winding and HV winding insulating material, and again LV winding, thick wire, LV, HV. Okay, let LV is 1 kilovolt, for example, just I'm giving. High voltage rating is 2 kilovolt. Then what is the dielectric strength of this insulating material? How much to be required? Difference. What is the difference now? 2 kV and here 1 kV. So this potential difference between the two levels we call here impressed voltage. Impressed voltage. What is impressed voltage? It is the potential difference between the two voltage levels. LV, HV. What is the difference? 2K minus 1K. So that is 1 kilovolt. This is the impressed voltage, a difference between two levels. So the insulating material, whatever we are placing, it should withstand the minimum voltage is what? Impressed voltage, that is 1 kilovolt. Then this is a perfect insulator. Then this is a perfect insulator. Okay. So in two ways you can understand about this dielectric loss. So one way is generally from HV to LV. What is insulator means? Isolating two windings. Is any current will pass through the insulator? No, zero. So if the dielectric strength, if dielectric strength of insulating material is greater than or equal to impressed voltage, then the insulator is a perfect insulator. There is no current at all in that insulating material. That is a perfect. But due to aging effect of transformers, aging means after 2 years of operation or 3 years or 4 years. So what happens to strength of any material? Strength of materials. So in mechanical engineering, this is one subject. Strength of materials. Now, strength of every material will reduce. Like that, the dielectric strength of this insulating material at the stage of manufacturing is 1 kilovolt only. But after 3 years, the strength little reduced. Now the strength is become 995 volts, not 1000 volts. Little strength reduced. But you are operating at same voltage levels after 3 years also. Now what happened? Dielectric strength become less than impressed voltage. During this insulating material will cause a small amount of current through this. It will cause a current now. Otherwise, previously no current because perfect insulator. Insulator means zero current. But now there is a small current because dielectric strength becomes less than impressed voltage. Now that small current we called displacement current. That is we call displacement current. Very, very small. Now whenever there is a current, resistance is very high. So there is some loss in the dielectric insulating material or not. So due to that small current, a small loss will take place in the insulating material. That is we call dielectric loss. Okay. So this is due to aging effect. And there is one more way to understand this dielectric loss. Listen. One more is, let this is high voltage winding. So two windings are separated by some insulating material. LV winding, HV, and this is LV. This is insulating material. Now every insulating materials like magnetic materials, however we have dipoles, here also we have dipoles like minus, plus, just like electrons poles we call them. In the insulating materials we have this electric dipoles we call electric dipoles. Now we are applying some voltage level 1 kV, let example HV is 2 kV, and the frequency is there some 50 hertz, positive half, negative half, positive half, negative half. So this is we call dipole, electric dipole. It is just like magnetic dipole in hysteresis loss we have seen. This is electric dipole. Now due to this applied voltage, across the insulating material, what happens is positive half, negative half, positive half, negative half. During that, these electric dipoles will interchange. Plus minus, again minus plus, like that for every positive half, negative half, they will interchange. However, dipoles, magnetic dipoles are orienting. Rotation is changing now one direction to other. In the same way, these electric dipoles also will interchange here. During that, these electric dipole consume a small amount of power. Consumes a small power, and this process of changing from one direction to other of these electric dipoles we call polarization process. This is called polarization. So what is polarization? The process of changing the orientation of this electric dipole for every positive half and negative half we call polarization process. So you should know in materials all this will come for engineering services people particularly. Just briefly idea I am giving. Now due to this polarization process, these electric dipoles are consuming some power. However, magnetic dipoles in hysteresis laws we seen in the same way, these dipoles also will consume a small amount of power. That is called dielectric loss here. That is called dielectric loss. Now, is this dielectric loss depends on, this is a constant loss or variable loss first? Constant or variable? Voltages are constant now always. Same voltage we apply to both windings. Voltage is fixed in windings always. So this loss also constant. Okay, whether there is load or no load, any condition, loss is constant. Dielectric loss is constant loss. Okay, it depends on voltage. Voltages are always fixed. So this is about dielectric loss. Remember these points. So aluminum tank you can use, but what is the strength of aluminum compared to iron or steel? Less, so not preferred. Okay. So actually this dielectric loss and this stray load loss is generally negligible loss, small amount. How much loss will take place in insulating material? Very, very small. So generally we neglect this. We never considered in our calculations. So while calculating efficiency, we never consider this. Only iron and copper loss. That's it. Okay. Just brief information given regarding this. When load increase, I2, I1 both increases. Load operation we have seen, no, in the load operation both increases. Whenever load increase, I2 increase, so I1 also increase, because we will supply to the load. Primary winding has to transfer the power to load. Okay, so this is about losses in transformer. Next, is starting tests on transformers. Tests on transformers. Tests on transformers. So whenever anybody asks to you, those who completed in your labs these transformers, and what is the test, you will tell directly. Yes, immediately it will come. First OC test, SC test. Okay, OC test, SC test. Then is it the only two tests we have? No. So there are so many tests on transformers we conduct at the factory levels, like manufacturing level. So many tests will be there in the R&D. And then in the lab level, only some three tests mostly we do in the labs. What is the three tests? OC test, short circuit test, and some nurse test. So mostly these three tests we perform in the labs. These three only we perform. But beside this, we have so many tests in the factory level. So let's see briefly first what are the total tests we are conducting on transformer. So there, first is polarity test. Polarity test. Second, open circuit test. Open circuit test. Third, short circuit test. And fourth, Sumner's test. Sumner's test. So anyhow, we will see only these four in our classwork also, because only these four we have in our syllabus actually for GATE ESC both. But additionally, in the factory level, we conduct some more tests. So they are like voltage ratio test, because on the nameplate of transformer we have voltage rating, primary voltage by secondary voltage. Then how they will give? By conducting this voltage ratio test. Voltage ratio test. Okay, next one more is winding resistance measurement test. Winding resistance measurement test. Winding resistance, primary winding will have some resistance, secondary winding will have some resistance. So they will conduct that test also to measure the winding resistance using Kelvin's bridge method, Kelvin's double bridge. And one more is insulation resistance measurement. Insulation, how much insulating material totally they used in terms of resistance, they calculate. Insulation resistance measurement test. In the factory level, these are all we don't conduct in labs, only these four mostly we conduct. Next, one more is interference level test. What is interference? So if you observe out in outside in our streets, the same distribution towers, the other people also will utilize to transmit, like cables, telephone lines, or DTH lines, or internet cable lines, anything. They will utilize our towers only, distribution towers. So beside that, transformers also there, no? Transformers also there. Beside that, only these lines also will go. What is the principle transformer is working? Induction. So as it is working on induction principle, whenever any communication line pass beside this, some interference will take place in communication lines, just like noise disturbance. That is interference in cables, particularly in these internet lines and telephonic lines. So here particularly interference will take place. That is called interference. How much interference this transformer is causing to the neighboring communication lines. That is called interference level test. If interference is more, out of this particularly interference level 8th one, and one more we have 9th one, that is noise level test. Noise level test. Out of these two, if they are not within limits, suppose interference should be as much as possible less. If it is not within limit, again it is sent to reconstruction. And one more is noise level. Noise, already we have seen humming noise in transformer. Humming noise. So whenever we operate transformer, humming noise is coming continuously. This noise also should be within limit. So there we have some decibels. In that decibels only, that noise should come, not more than that. If noise is very high, that is not desirable. Now, if noise is more, what will be the problem? Tell me mainly. Suppose if noise is coming more in the transformer, when they check, what is the problem? What is the problem? If noise is more, what is the problem in transformer? Yes. If noise is more coming or more noise coming from transformer means the main reason will be staggering. Staggering is the problem in transformer. It is not perfectly done. Stagger means core laminations properly not attached, so that more noise it is giving. Then what they will do? Again, they will send to clamping. Tightly, they need to attach some clamps such that noise will reduce. Otherwise, still noise more, then completely they has to open laminations and re-staggered with properly insulating materials. So up to that, they will reduce as much as possible noise level. So that is called noise level test. But these are all factory level. We don't do in our lab level. So in lab level, mostly we do OC, SC, Sumners. Polarity also we don't do mostly in the labs. Very few they will conduct this polarity test. But as a electrical engineer, if you select in any PSUs during training period, mostly in every PSU during training period, we have to conduct polarity test. We have to conduct polarity test on transformer. Very important and very easy also it is. But we don't know how to conduct polarity. Polarity means what polarity test? To mark dot polarity. To mark dot polarity. So we are marking now primary side dotted terminal, secondary side dotted terminal. So that dot marking polarity is important. And what is the need of this polarity test? For parallel operation. For parallel operation, we are conducting polarity test. That's it. Okay. So one by one, we see these four tests. First, let's see polarity test. Taken all of you this. Hopkinson test, Swinburne's test. These are all DC machine tests. Yes. See the first one, polarity test. Right. First one is polarity test. See, for your examination, particularly in GATE examination, the questions is possible mostly from only these two, OC test, SC test. That's it. Okay. From these two only you'll get questions. But for engineering services, each and every point, each and every line, there is a chance to get question. So I cannot say this is important for engineering service. Polarity test also they may give, or Sumner's test also may they make. Okay. Everything important for engineering service. Right. Polarity test. Suppose there is a single phase transformer in front of you. Now you need to mark primary side dotted terminal, secondary side dotted terminal. How to mark this dotted terminal? Okay, for this we are conducting this test. So very easy test. First consider a two winding transformer. Consider a two winding transformer. Okay, and there is some voltage rating on this. Voltage rating is there. Voltage rating is there. Let primary voltage E1, secondary voltage E2. Voltage rating given E1 by E2. On the nameplate also it is there. Voltage rating. and we need to mark primary dotted terminal, secondary dotted terminal. Okay, only for parallel operation it is. So what is the problem if polarities are not properly connected? So we will see in parallel operation what happens it is. Now the procedure for this is, let us assume the primary terminals as a1 a2. So anything you can take p1 p2 anything x1 x2 whatever. So I'm taking primary is a1 a2, secondary is b1 b2. Okay, a1 a2 b1 b2. Now out of this a1 b1 and a2 b2, so let us short any two terminals. Any two you can short, like a1 b1 I'm shorting. I will short now a1 b1, I will connect directly these two I am joining, and across a2 b2 we need to place a voltmeter. Across a2 b2 you need to place a voltmeter. Okay, anywhere you can do this. Suppose place between a1 b1 voltmeter, both are same only, and short a2 b2 here, anything you can do. And let us connect a rated voltage to primary, give supply to primary. How much voltage you have to give? Supply voltage, whatever is there, E1 here. Suppose the voltage rating on the transformer is 400 volts by 200 volts. Then how much voltage you will give to primary side? Apply 400 volts, that voltage having rated frequency. Now this is 400, this is 200, and this voltmeter will read some reading based on that your polarity. The procedure is, let us consider out of a1 a2 any one is the dotted terminal. Primary side your wish. Primary is your wish, anywhere you can put dot. Suppose I am considering a1 is the dotted terminal, this is my dotted terminal, and secondary side I need to mark dot, but you should not mark directly it is. To mark secondary dotted terminal, you should observe the voltmeter reading. Suppose if this voltmeter read sum of voltages E1 E2, sum means E1 plus E2. What is E1 plus E2 means? 400 plus 200, 600. So if the voltmeter is showing 600 volts, then assign secondary polarities opposite to primary. Means if a1 is dot, don't consider b1 is dot, then b2 will be the dotted terminal. Additive means when additive it is plus minus, when you connect additive. Or if you take dot here, then this is plus, this is also plus, then subtractive nature. No, subtraction means you should get here 200, but you are getting 600, so you should not place dot here. Where is dot now? b2 is our dotted terminal. Okay, now if same voltmeter if reads the difference of voltages, if the same voltmeter is reading difference E1 difference E2, then how much it is? 400 minus 200, 200 volts. If it is difference, then how to assign secondary? See, if it is sum, then assign opposite polarities on both sides. Opposite means if a1 is dot, then b2 is dot, opposite. And if it is difference, you need to assign same polarities on both the sides. Same polarities. If it is a1 dot, b1 also dot. Okay, like that we need to assign polarities on this transformer. So this is easy, simple test. Just voltmeter is required for this. Enough voltmeter and source is required. And based on that voltmeter reading, you can put dotted terminals on primary and secondary winding. But there is a drawback in this test. In this procedure, there is a small drawback. Okay, first write the procedure for this, then we see what is that and what is the remedy for this. Take the figure first. Take the figure quickly. If noise is more in transformer, what is the problem? Suppose you are working on the transformer, you are doing a test. It is creating very high noise. Is it desirable or is it uh, interested to listen that noise? No. So it is like a disturbance we feel, irritation. So noise will create noise pollution. That is one problem. And other main problem is If noise is more in the transformer means vibrations are more in that. So due to that, windings may get little dislocation because winding is on the core. If core is vibrating, windings also vibrate. So there is a problem, dislocation of windings may possible. So these are all problems with more noise. So we need to reduce as much as possible noise. Maybe if you remember also in your lab while conducting OC test, those who are in now second year or third year, if possible, I think maybe that lab test will be there for some of you, transformer test. While conducting OC test, whenever voltage rating slowly increases, noise in transformer you can observe increase. Slowly it will increase. Because when voltage increase, main flux magnitude increase, then automatically the vibrations will, whenever voltage increases, flux increases, so little vibration also might increases, so noise is rises. You can observe this is in the labs. So as much as possible, those who are right now in second year or third year, so go to your lab, use effectively your lab to learn machines well, particularly DC machine, all transformers, synchronous machine, induction machine. Ask them to show each and every part of machine. That is the first thing you have to do. But you never do in the lab, that is. Now here you will struggle. You want everything here itself. How it is possible? Without learning anything practically, how much you can learn theoretical? It is difficult to learn theoretical everything. But once you see practical, suppose transformer parts I have shown, same if you directly observe, no, with your physically directly in front of you, you will get so much information regarding that, and that will be remembered for long time also if you see directly while learning like this. Okay, so try to go your labs now, ask them to show each and every part. So don't hesitate there, don't hesitate. So people will have some feeling that if we ask anything, they may reduce our marks like this. So these are not important, marks are not at all important. If they want marks, give them. You don't want marks, just pass is enough. Who want marks without having any knowledge? What is the use of marks? Question yourself first. Okay, try to go your labs and try to ask them to show each and every part of every machine. Those who are now right now in second or third year or fourth year also. Okay, so once you step out from the college, nowhere you cannot see anything, only induction machine you can see outside in service shops, that's it. So better than this, ask them in the labs to show each and every part of machine. Particularly DC machines, they're only possible to show outside, very less we are using, no, domestic purpose. Write the procedure for this. Procedure. Right, first point, assign the primary and secondary terminals. Assign the primary and secondary terminals like A1, A2, B1, B2 we taken terminals. Assign the primary and secondary terminals as A1, A2 and B1, B2 respectively. Next, second, short A1, B1, short A1, B1 and place a voltmeter between A2, B2, between A2 and B2. Short A1, B1 and place a voltmeter between A2, B2. Next, apply rated voltage to primary. Apply rated voltage to primary and assign and assume primary polarities. So primary, our wish. You can assume primary polarities always. Apply rated voltage to primary and assume primary polarities. So how we assume primary polarities? As A1 is dot, we consider A1 is dot, we take Now, fourth point. Now, what is next step? Now you need to observe voltmeter reading. If voltmeter reading is some, then assign the secondary polarities opposite to primary assumed polarities. Right. Fourth point. Fourth. If voltmeter reads, if voltmeter reads sum of voltages, then then assign secondary polarities, then assign secondary polarities opposite to primary polarities, opposite to primary polarities. Okay, if voltmeter reads sum, then assign secondary polarities opposite to primary polarities. Means if a1 is dot, a1 is dot taken, then which one should be dot? B2 should be dot. Okay, and if it is difference, if a1 is dot, b1 also dot, same polarities you need to assign on both primary and secondary. Okay, make a note. So there is a drawback. I said, what is the drawback is observed. Observe drawback. The drawback in this procedure is, see, just example, I taken a small voltage rating 400 by 200. Suppose now I have a transformer 11 kV by 33 kilovolts. This high voltage rating transformer 11 by 33 kV. Then can we use the same procedure for this voltage rating of transformer? No. If we use this procedure for the same 11 kV by 33 kV transformer, your voltmeter will damage first, because what is the voltmeter range available maximum analog voltmeters in your labs? Also you can see that 0 to 600, actually 0 to 300 scale multiplication 2 will be there. Is up to 600 you can measure. If it is very high voltages like 33 or 132 220 kV, is voltmeter available in the range to measure some or difference? Not at all. Voltmeters at higher levels may not be available. Then we cannot use this procedure. Then what is the procedure to be used? Yes, we have other procedure in order to find polarity for any high voltage rating transformer, not only high voltage, for low voltage also you can use that. Okay, first write that point. The above procedure is not suitable. The above procedure is not suitable for high voltage rating transformers. For high voltage rating transformers, due to unavailability of voltmeters, due to unavailability of voltmeters, voltmeters in that range, in that range. Okay, we should not use this procedure for high voltages, because voltmeter also you require that much capacity, but that is may or may not be available. For that reason, avoid this procedure for high voltages. Then what is the procedure we use? So there is one procedure, therefore the procedure used is, the procedure used is called, the other procedure we use, that procedure is called DC kick test. DC kick test. DC kick test. Kick test. Simply we call kick test it is. Now let's see who will give kick here. Why we call kick test it is. Side heading DC kick test. DC kick test. This is one of the method for polarity test. DC kick test. Observe now. Again, take the same two winding transformer. Taking the same two winding transformer. Okay. And here, same as the previous procedure, assign the primary terminals A1, A2, secondary B1, B2. Okay. Now here we will place a switch and a supply is given to the primary, which is a DC supply, not AC supply, which is DC supply. Now switch is placed in between the source and winding, and secondary side B1, B2, we will short circuit through an ammeter. We short circuit through an ammeter. So this is ammeter. This is ammeter, and this is ammeter pointer. There is some scale on that. And the type of this meter, ammeter, is MC type, moving coil type we call. Moving coil type. MC type it is. And those who are in second year, you may not complete these measurements, I think. So we have two types of meters, MI instruments, MC instruments. MC type. MC is used for DC measurement, and MI is used for AC measurement mainly. Okay, MI instruments for AC, MC we use for DC measurement. Okay. Now there is EMF on primary E1, E2. Clear. Observe first. First of all, can we apply a DC voltage to transformer? To transformer, can we give DC? Yes, we can give. But what happened? What happened if we give DC voltage? People will say transformer winding will burn. Yes. Observe here. Actually, we should not give DC supply to transformer windings. So there are two cases again, practical case, ideal case. So you may get question, if DC supply given to practical transformer, what happened? If DC supply given to ideal transformer, what happened? Ideal means what is the resistance of winding? Zero. So if we give DC supply, first practical case we observe. See here what happened. Practical case. When some DC voltage is given, some voltage V1 DC. What is the switch closed? What is the current flowing through this winding? DC current, no, it is not alternating. DC constant. Winding is stationary on the core. Winding will never move here like rotating machine. Winding is fixed, and whatever the current flowing, that is also fixed, DC constant magnitude current. And whatever the flux produced, according to right hand thumb rule, if you apply, whatever the flux produced, that is also DC constant. Then what is EMF induced according to Faraday's law? Rate of change of flux. Is there any change in flux? No, zero. Therefore, EMF induced is zero. So whenever there is EMF, actually, whenever there is EMF, this EMF will oppose the cause. See, actually in transformer, primary current is what? I1 equal to V1 minus E1 by impedance of that winding. AC case. Normally, when we apply AC, this is the equation I1. If you apply a 200 volts supply, E1 is almost nearly same, like 197, for example, divided by some impedance 0.5. Okay, how much it is? Then 3 by 0.5 or 1 by 2. This is 6 amperes. Or I1 is very, very small. So no problem to winding, it will work. But when you give DC, now what is the DC current? IDC equal to, is there any EMF here? 0. So V1 minus 0 by only resistance. So DC means we never take reactance component. Only DC means resistance of winding. Now how much it is? 200 divided by what is resistance of winding generally? Less than 1 ohm. Very small. So take zero point 0.1 small resistance. Then what is this value? 2000 amperes. But how much actual current it is flowing in AC case? Just 6 amps is flowing. But now 2000, very, very, very high current. So if this much current flows in the winding for some duration, the heat produced is very high. I square R. The heat produced is very, very high due to the transformer winding completely melt. That is, we call the transformer winding will burn. Transformer winding will burn. So we should not apply DC voltage to transformer windings practically. What happen if you apply? Windings will melt or burn, damages. So practically we should not apply. But ideally, can we apply? Ideal case, what happen? Yes. In ideal case, if you apply, ideal case also, if you apply, what is EMF? 0. Then what is the current IDC? What is the current IDC? IDC equal to VDC by 0. Resistance 0, no? Then what is current? Very, very high, infinite. Then winding will damage. Tell me, winding will damage? No. No damage to winding. No problem. You can apply, winding will not damage. Continuously current increasing, flux increasing. So core enters into deep saturation. But winding will not damage. Why winding will not damage? So no damage to transformer winding here. Why it is not damaged? Because as resistance 0, is there any loss in this first? No loss. If there is no loss, is there any heat in this transformer? No heat. So no damage to transformer. So continuously current increase, flux increase, it will take place continuously, but no damage to transformer. So ideal case anyhow not possible, na, it is practically. So practically we have to think, whenever you apply a DC voltage practically, EMF induced is 0, so no opposition to supply, so very, very high current is flowing. If this high current flows for some duration, the loss is very high, finally windings will burn. So you should never apply DC voltage to the transformer windings. Then why we are applying DC in this test? Yes, you can apply DC. How can you apply DC? You can apply DC with some protection system. That's why we taken a switch here. Now what we do here is, observe carefully. Observe this. So primary side A1, A2, secondary B1, B2. Secondary is shorted. Shorted means if there is a EMF, current will flow. And based on current direction, how current will flow? Like this, B1 to B2 like this, or in this way, B2 to B1 like this. How current will flow? We don't know, na, that is in what direction current will flow. That depends on EMF polarity. So we don't know in which direction current. That's why MC. So what happened in this MC meter is, if current flows in positive direction, one direction, pointer will deflect from, this is 0, let this is 0, let this is 5 ampere. Current will, this pointer will deflect in this clockwise direction. But whenever current flows in reverse direction, no, then this pointer will deflect little in the backward direction. Little, because a pointer cannot go beyond that. So there is left and right hand of in the scale. So 0 will be there. Actually pointer is 0 at 0 position. But whenever pointer is deflecting back means little, it will go back. That's it, and stop. Okay, because it cannot rotate like this circularly. Little it will go back and come back to 0 position, same position. Now see what happened. Let us assume primary polarity. So primary side our wish same as previous. A1 I am taking as dot. A1 I am taking as dot. Now close the switch. Let us take some small DC voltage is enough. 10 volts I am applying. A small DC voltage enough. So I am closing the switch. Close the switch and open at the same time. Close and open at the same time. During that closing and opening of switch, your eye contact must be on this meter. Your eye contact must be on this meter at that time, because whenever you close the switch and whenever you open, your ammeter pointer will, suppose 0 it is, your ammeter pointer will go forward and come back, or it may go back and come back. When you close and open, it will go and come back, or it will go and come back. That is called kick given by meter. The pointer will give kick here. It may give forward kick, it may give forward kick, or it may give backward kick. Any one it will give, either forward or backward. So when it is forward, then you have to take B1 also dotted terminal, or when it is backward, you have to take B2 is the dotted terminal. Now what happens here is, observe carefully once. We are not applying DC for long time. Long time you should not apply. For 5 seconds also you should not apply. Just close and open. Then this pointer will deflect and come back. Why pointer is deflect first? This is ammeter. Okay. Why pointer is deflect? Because current is flown at that time. How current is flown? Without EMF, is the current will flow? No. Then how there is EMF? Yes, there is EMF. How EMF induced due to DC? Yes, induced. Why? Because when switch is closed, current is flowing suddenly. Current is flowing or not? Yes, current is flowing. Now, whenever there is a current in the winding, flux will produce. Some flux will produce. Now, suddenly when you open the switch, current 0. When current 0, suddenly that flux will decrease to 0. Means you created a change in flux in the core or not. You created a change in flux in the core. Flux is initially increased when switch closed, again decreased. So there is a change in flux. So EMF induced on primary and also on secondary. So that flux is there in the core at that instant, suddenly. Then EMF induced in both. When there is E2, there is a flow of current in this secondary set. Based on the direction of current flow, this ammeter will deflect. Our ammeter will give a kick here. Why we call kick? Pointer initially 0. Now it won't rotate smoothly like this, and it won't stay at any point. What happened when you close switch and open? The pointer will go to some value and come back. It will go to some value and come back immediately. That is called kick given by ammeter or meter simply. See, if ammeter gives forward kick, if ammeter given forward kick, then assign same polarities on secondary, just like primary. If ammeter given backward kick, then assign opposite polarities on secondary with respect to primary side. Okay. First take the figure. See, right now I cannot see your messages, whatever, because there are 1500 messages. Very difficult to watch me it is. See, one more time this test. Primary side we are applying a DC voltage through a switch. Secondary side we shorted with a ammeter. Okay. Now primary side we assumed A1 is dotted terminal. Secondary we need to mark. So for that, this DC voltage we are applying through a switch, just closing the switch and open. Why we are not applying continuously? If you apply for long time, what is EMF induced? 0, because rate of change will become 0. EMF, because flux will become constant. First, if you apply for some duration like 10 second, 15 second, if you apply, flux is constant, EMF 0 there. Then even EMF 0, current is very, very high. Then windings will damage. For that reason, closing and opening. During that, this pointer will give a kick, either forward or backward. Then based on the kick given, we need to assign the polarities. Clear? Write the procedure simply. Write procedure in simple 2 lines. Procedure. Apply a DC voltage apply a DC voltage to the primary through a switch short circuit short secondary terminals through a ammeter through a ammeter. Okay, next, assume primary polarities. Assume primary polarities. So that is A1 we taken dot example. Assume primary polarities. Then close the switch. Close the switch and open momentarily. Close and open momentarily means at the same time. Just closing and opening. Close the switch and open momentarily, comma, during this observe the kick given by ammeter. The kick given by ammeter. The kick given by ammeter. Next. Next line. If ammeter shows forward kick, then assign secondary polarities. As same as primary polarities. Primary polarities. Otherwise means backward kick. So directly I'm writing otherwise opposite polarities. Means backward. For backward kick, opposite polarities you have to take. So this procedure or this test is suitable for any voltage rating of transformer. And one more is you need to take care of this test. If you close the switch and forget to open, then definitely you will come after some time because of the smell coming from the transformer, because complete winding has burned. So take care of this. Close and open at same time. Okay. Never apply DC voltage for long time or never apply DC voltage continuously. If you apply, definitely transformer windings will burn or damages. Switch is not having any sparking because at that time, what is the DC voltage we applied? That's why we taken a small voltage. Induction effect will takes place. Just now I said whether it is DC flux also, you are creating like change in flux these days with respect to time closing and opening. During that time, flux increase and decrease to zero. No, that's why EMF will induce in the winding at that instant because you created variation of flux. Whether it is DC flux also, you created variation. There is a transformer action. Okay. Yes, primary side your wish. Any polarities, any terminals you can take as dot or undot. And secondary depends on your assumption of primary side. Okay. So this is polarity test, and there is no use of this polarity test like if you take single transformer, no, it is not for load connection. Anywhere you can connect load. Suppose there are two wires from transformer secondary. Anywhere you do supply AC supply, you no need to check any polarities further. But only the thing is, when we connect two transformers in parallel, we should check the polarity. Very, 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 very important. The most important condition for parallel operation is only polarity. So that question is also you will see. The most necessary condition for parallel operation is only polarity. First preference is for polarity only. If polarity by mistake wrongly connected, you can forget about your transformers, because transformers will have severe short circuit currents like a circulating current. Complete windings will damage. So polarity is very important. For that purpose only we are doing polarity test, and there is no other use of polarity test. Okay. So take break for again 15 to 20 minutes, and then we see OC test, OC, and mostly SC test today. Okay, take break. Okay, mostly you will take class up to 8:30. Okay. See, the next test is open circuit test on transformer. So these two tests important, OC test and AC test. Sumner's test is not important for gate, but only for engineering services that is required. Okay. See the second one, OC test, open circuit test. Open circuit test, or simply we call OC test it is. Open circuit test or OC test are also called no load test. Also called no load test. No load test. Now, first, what is the main objective of this test? Objective, or what is the purpose of conducting this test on transformer? Why we are conducting? Objective. So mainly, we have two losses in transformer. Now, what is that? One is iron loss and copper loss. Now, iron loss we calculate in OC test, and copper loss we can find in short circuit test. Because in OC test, iron loss depends on what mainly? Voltage. So if you apply rated voltage to transformer enough, you will get iron loss. And how to find copper loss? To find copper loss, there should be current in both windings. So when currents will flow in both windings? Only when you connect load. But here we don't connect any load, just we short circuit and then we conduct the test. Short circuit means don't say that it will get short circuit or it will get damaged. So accordingly, with protection only, or with whatever the care we need to take, by taking the care itself, we do short circuit test. Okay, short circuit means not it is damaged, it is short circuit with care. So that we need total copper loss of transformer. So iron loss we calculate in OC test. And one more other objective of this OC test is uh, to if you remember, we have seen equivalent circuit of transformer previously. Equivalent circuit. So there we have two types of parameters in that. Suppose if it is asked to find primary current of transformer, suppose primary current from the equivalent circuit, you can find or not? Yes, we can find. From the equivalent circuit of transformer, you can find primary current, or whatever is required, you can find from that. But to find from equivalent circuit, you should know the circuit parameters or not, like R1, X1, R2, X2, R0, X0. All these parameters you should know the values or not. Yes. So that values in the equivalent circuit, we have mainly two types of parameters. One is called load parameters and other is no load parameters. Two branches we have, load branch, no load branch, are also called series branch and shunt branch. So maybe you remembered, I hope. So in series with load, we have R01, X01. In parallel with that, we have no load parameters, R0, X0. So that no load parameters we calculate in this test, OC test. And the load parameters we will calculate in next one, short circuit test. Okay. So write that objectives. First objective. Objective means purpose of this test. First one is to find iron loss, iron or core or constant loss of transformer. Constant loss of transformer. See, same OC test and SC test you will get in induction motor with other names like no load test of induction motor, block to the rotor test of induction motor. Same as it is similar to this OC and SC test. However, we will see here same you will see in induction motor again. Okay. Here, if you understand well, there the test no load and block rotor test are very easy. So these two also very similar for transformers and induction motor tests. Particularly these two tests, no load test and short circuit test. Okay. Next, second objective, to find no load branch parameters. No load, also called shunt branch, it is. Shunt branch parameters. What are the shunt branch parameters? They are R naught and X naught. These two we will calculate in this test. Okay. Next, one more objective we have. This third objective is important for direct numericals also. In previous gate also we have one question on this. And in engineering services and competitive examinations, directly we are getting questions on this third point. What is that point is observed here. In the first objective, what is that? To find iron loss. So iron loss you are calculating in first objective. Yes, you got iron loss. Now, iron loss is sum of two losses or not? Yes. What are that? Hysteresis loss and eddy current loss. So you should know what in the total iron loss, how much is hysteresis, how much is eddy current. So that is called separation. Separation of iron loss into hysteresis loss and eddy current loss. So for that separation also same OC test again we conduct with a little modification. This is also a lab test. This is completely in same OC test is a lab test. All these three you will do in the lab. Okay. Third is to separate iron loss into hysteresis and eddy current loss. So this is third one little important. This procedure little important. You should concentrate in third. How to separate iron loss into hysteresis and eddy current loss. So remember for induction motor, one more point I will just tell you here. You remember whenever it is. Okay. What is that is in induction motor, same no load test. What is the objective of that no load test? To find constant loss. But in induction motor, constant loss of motor means iron loss plus mechanical loss combinedly. Some of these two we call constant loss there. Mechanical loss is a constant loss in induction motor. Why it is, you will see there. Okay. So constant loss of induction motor means what? Sum of iron and mechanical. What is the constant loss of transformer? Only iron loss. Now, in that induction motor no load test, you need to separate constant loss into iron loss and mechanical loss, because you will get total constant loss. You will get total constant loss there. But in the total, how much is the iron? How much is the mechanical? That is also you need to separate. But here we don't have that. Only iron loss is separating hysteresis and eddy current. That's it. Okay. Remember this point you will get additionally in induction motor. So like this, you need to compare the similarities between one machine to other so that easily you can understand there again. Otherwise, if it is not raised these points now, there you will get see that the points again like newly. So if you know already, so you will get direct idea there. Yes, we need to find this. That is the objective of no load test in induction motor. So you should relate machine to machine so that some topics gets easy there. Okay. So this is the objective of OC test of transformer. Now let's see which side this test is required to conduct. So first of all, as we need to find iron loss in this test, we should apply rated voltage to transformer or not? Yes, because iron loss depends on what? Voltage rating. If you want total iron loss, you need to apply rated voltage of the transformer. Suppose on the nameplate you have some 400 by 200. You need to apply rated voltage. Anywhere you can do the test. LV side you can do the test. HV side you have to apply rated voltage. Okay, so write that point here. This test should conduct at rated voltage and rated frequency, to calculate the total iron loss. Otherwise, if you don't apply rated voltage, suppose if you apply low voltage, then do you get total iron loss? No, iron loss depends on what? Voltage. If you apply total voltage, whatever is there on the nameplate, you will get total iron loss of the transformer. So we have to conduct the test at rated voltage and frequency. Okay. Now let's see. Which side the test is preferred to conduct. So I'm taking the transformer figure. So draw the figure simultaneously. Transformer is having two sides, LV side, HV side. No. Now, which side we need to conduct the test? That is important. See, I'm taking this is LV winding. Let it is HV winding. This is LV and this is HV. Low voltage winding, high voltage winding. Now, so for example, I'm giving some rating. Let low voltage means 200 volt, high voltage means 400 volt. For example, some rating I take. Now, no load or open circuit test. One side you need to give source or supply, other side should be open. Now, which side is best or preferred to give voltage, supply voltage? LV side or HV side? First of all, can you give any side or not? Yes, you can give any side. One side you should give supply, one side should be open or no load on that. And that is a open circuit test. Now, where it is preferred to give supply, LV side or HV side? We need to give rated voltage anywhere. If you want to give LV side, you need to apply 200 volts supply voltage. You need to give a source of 200. Or if you give supply on HV side, how much voltage you should apply? 400 you should apply. Anywhere you can give, no doubt. You will get same iron loss anywhere. But we preferred to give supply to the LV side with open circuit on HV side. We preferred to give supply on LV side with open circuit on HV side due to some advantages. Let's see what are the advantages. So these advantages itself in some of the competitive examination direct questions. What is the advantage to conduct the OC test in LV side? Why we should conduct? What are the advantages? So what happen if you conduct test on OC HV side? So all we will observe here. See, I'm connecting meters first. So 1 wattmeter required in this test to measure the power drawn by transformer, because transformer will draw some power under no load also. That is equal to what? Loss. Why loss? We know input power is always output power plus losses. Okay. Now output means secondary side you are not connecting any load, just to open. So what is the output? 0. But you are giving some input power or not? Yes, you are giving some input power. That is equal to losses. Whatever the power drawn by transformer, that is equal to losses itself. Under no load, power drawn by transformer equal to loss. What loss that is? What loss? Losses is what? Mainly iron plus copper. But as it is no load, how much current it will take? A small current called no load current, I naught, very, very small. So if you neglect that copper loss, because current is very small in that, then mainly it is iron loss. So total power drawn by transformer is equal to iron loss. Then who will measure that? This wattmeter will measure. So wattmeter to measure power drawn by transformer. Okay. Next, 1 ammeter required to measure how much current it is drawing, and 1 voltmeter is required to measure the voltage applied to transformer. And this is we are applying from an auto transformer, variac we call, or dimmer stat in the labs we call it is. Okay. All of you aware of this variac now, auto transformer, those who are in second and third years. So this is our auto transformer, means variable voltage we can give from auto transformer. This is also called variac, variable voltage supply. This is our main supply, and this is slowly we change. You will rotate slowly step by step. This is 0, and if you move the pointer towards upward direction, number of turns increase, voltage rating also increase. Okay. So we required 1 voltmeter, 1 ammeter, and 1 wattmeter. W naught, I naught, V naught. 3 readings we will take here. Only 3 readings. Tests are very, very simple. OC test, SC test, very simple. Only 1 reading we take. Only 1 reading. So calculation is important from the readings. First observe, we preferred to conduct the test on LV side with open circuit on HV side. With open circuit on HV side, because see the advantages why. how much voltage you need to apply on LV side? Rated voltage. What is the rated voltage of LV? 200. So whatever the source you need is low voltage supply. You need a low voltage source because 200 only required to apply now. Otherwise, if you conduct the test on HV side, how much voltage you need to apply? 400. So voltage source capacity increases. So this is easily available low voltage source compared to high voltage source. Okay, this is one advantage. Next, second, you are placing one voltmeter here, voltmeter, to measure how much voltage you are giving to transformers. Then what is the capacity of voltmeter required? Low capacity voltmeter is enough or not? Yes, enough. Why? How much voltage you need to measure? 200 volts you need to measure. So low rating meter is enough. If you conduct the test on high voltage, you need a meter of 400 volts. High capacity required. Range is required more, but here not required. That is one advantage. And the main advantage is, okay, no need to worry. I will write all the advantages again. Just listen. One more advantage is, see, LV side, what is the rated current? Low voltage means high current. For example, 100 amperes. Rated current or full load current it is. And HV side, what will be the rated current? It will be 50 amperes. Okay. Volt ampere same. Calculate if you want. 200 into 100. How much? 20k. 400 into 50. 20k. So volt ampere is same on both the sides. So accordingly, I take an example. Now, if you conduct that, these are the full load currents. 50 is the full load current on HV. 100 amperes is the full load current on LV side. If you conduct the test, if you conduct no load test, what is the current drawn by transformer? I naught. What is the percentage of I naught approximately? Previously we have seen. No load current is 5 to 6% approximately. So 5%, let us take 5%. What is the 5% of 100 amperes? 5 amps. Okay. What is the 5% of this 50 ampere? 2.5 ampere. 2.5. 5% of 100 is 5 ampere. 5% of this 50 is 2.5 ampere. So if you conduct test on LV side, what is the magnitude of no load current compared to HV side? No load current magnitude is 5 ampere, which is greater than this 2.5. Like that, if you take some other transformers, magnitude of no load current on LV side is little greater when compared to high voltage side. Suppose there are some transformers like high voltage side, rated current is 10 amperes. So I will take one more example so that clearly you will understand. See, so I'm taking one more. Let this is 10 amperes. Full load current is 10 amperes. Now what is this 4 kVA? Then here, how much we have to take? 50 or what? Yes. Twenty amps. Okay, for example, take still better values. I will take voltage change. I am changing voltage. So let us take, this is 1000 volts, high voltage, and 10 amps is the rated current here. Then what is 1000 into 10? 10 kVA. Now 10 k by 200. Calculate how much? 10 k by 200. Nothing but 50. 50 amperes. Okay. So example I taken a 10 kVA transformer. 10 kVA, 200 by 1000 volt transformer it is. LV is 2000, HV is 1000 volts. Okay. Then if you find the full load currents, how to find full load currents? Volt ampere rating by voltage. 10 kVA by 200, 50, and 10 kVA by 1000, 10 amperes. So these are the full load currents on both sides. But as it is no load test, no load current drawn by transformer is how much? If it is LV side, 5%, anywhere 5% only it will draw. What is 5% of this? 2.5 amperes. 5% of 50. Now what is 5% of 10 ampere? 5% of 10 ampere, 0.5 ampere, very small current. So observe now, if you conduct test on LV side, what is the magnitude of no load current? 2.5 amperes. Then in this ammeter, how much current you need to measure? 2.5 amps you need to measure. But if you conduct the same test on HV side, this side, how much ammeter here has to measure? If you place a ammeter, that ammeter should measure 0.5 ampere. Now tell an ammeter or any meter, particularly MI instruments we are using, AC it is MI. What is the scale of MI instrument? Scale. Is it uniform scale or non-uniform? This is non-uniform scale. Non-uniform means how the scale generally? Scale. See, this is 0. Directly here they will give 1, because in between they don't indicate any lines. Directly 0 to 1, then 1.1, 1.2, 1.5, like that 2 and 2.5, like that scale will be there. And again at the end of the scale directly they will give some reading. This is non-linear scale. Means in this non-linear scale you can measure higher values accurately, but not small values. Small means 0.5 you need to measure. Where is 0.5? This is 1, this is 0. 0.5 means can you take at the center? No, that is wrong. That is not at middle. Non-linear scale it is, not uniform scale. So at the center is wrong. That's why you will get errors in the readings. But if you conduct the same test on LV side, how much ammeter should measure? 2.5. Now this is little higher value, no? Yes, as it is little high value, 2.5 means it will come exactly in between somewhere. So accurate reading is possible to measure. So what is advantage? If the test is conducted on LV side, the magnitude of no load current is higher compared to HV side, which can be measured accurately. But it is difficult on HV side because we may get errors in the calculation of readings. That's why we preferred to conduct the test on LV side always. Okay, right now. Right. These are all just example to understand clearly. Right here, this test is preferred to conduct. This test is preferred to conduct on LV side. To conduct on LV side with open circuit on HV side. With open circuit on HV side. Due to the following advantages. Due to following advantages. Following advantages. So write the first point. What is the first advantage if you conduct an LV side? The supply required, voltage source required is low voltage supply. Right there. It requires a low voltage source. It requires a low voltage source which is easily available for us. A low voltage source is enough. Next, the voltmeter required is low range capacity. It requires a low rating voltmeter. A low rating voltmeter, easily available. This is also. Next, third one, the no load current. The no load current can be accurately measured. The no load current can be accurately measured on LV side, compared to HV side. Compared to HV side. Okay, we can measure accurately the current because it is higher value when compared to HV cell. So due to these advantages, we preferred to conduct test on LV. Otherwise, if you do the test on HV also, you will get the same values. Values will not change. Iron loss will not change. Same iron loss you will get. But there, what is the problem? High voltage source required, a high rating voltmeter required, and the no load current is small. That may be measured. That cannot be measured accurately in meter. Small readings is difficult for us. It is difficult to measure small readings, small values in the meters because non-linear scale the instruments having. Okay. Now see the procedure. Taken all of this. See the procedure. Procedure. What is the procedure? Procedure means the engineering students very well know about the procedures because of good experiments, experience in the labs. We write very well. What is that? Connect the circuit as shown in figure. Okay. Avoid loose connections. So some 3-4 points every experiment we can write easily. Connect the circuit as shown in figure. Avoid loose connections. Take the readings without parallax error. Okay, but the main points we don't write. What is the main procedure? And remember this point: those who will write conventional examinations after engineering services prelims examination, if you qualify, or any junior engineers conventional examination, anywhere conventional examination, when you are writing, suppose if they ask, mostly in that conventional, they don't ask about explain complete OC test of transformer. They don't ask like this. They will ask out of these three objectives, any one objective to you, like explain the procedure to find iron loss by conducting OC test. So only that first objective, how it is, you have to write. For that, you need to draw a proper figure and proper procedure. While writing this procedure, don't build big lines there because only in our engineering that is suitable. When you write the quantity is more percentage of marks you get. But here quantity not important, quality only important. So in this engineering services particularly, quality only important. Write your procedure in 2 steps or 2 lines, you will get full marks. Suppose if it is given for 20 marks, you write the procedure and all only in 2-3 lines, you will get full marks. And the other person who written in 2 pages the procedure, he will get 2 marks. Remember, he will get 2 marks only because that much patience they don't have to read all your theory line by line by line there. They will read whenever they are reading in 2-3 lines, you should give the complete information in the 2-3 lines itself. That's it. Then they will give full marks. Okay, so avoid all these points from now. So that habit now again you should build. So after engineering you should build this habit again because we are habited to that writing so many lines to fill the pages, but not here. The procedure is very simple. See, apply rated voltage to LV winding. What is the rated voltage of LV winding here? We take an example 200. So 200 you have to apply by using auto transformer. Slowly apply the voltage. By observing what? Voltmeter you have to observe. Voltmeter will show how much voltage you are giving with open circuit on HV side. Then once the voltmeter is showing rated voltage, take the readings of ammeter reading and wattmeter reading. Enough. Only single reading we take. Test is over. Now calculation we have to go. And one more thing, the wattmeter, the type of wattmeter required in OC test is LPF wattmeter. So we have two types, LPF meter, HPF meter, high power factor or unity power factor we call. Low power factor meters, because in the previous classes also I said no load case. What is the power factor of transformer under no load? Less than 0.5. So if power factor of any device is less than 0.5, you have to use LPF. if the power factor is greater than 0.5, you need to prefer HPF meter for accurate measurements. Okay, so in OC test, which type of watt meter you need to take? LPF. Remember, this is also important. Previous gate also it is there. The type of watt meter required is LPF because power factor here is less. Okay, then accurate measurement possible. Otherwise, if we take HPF, it will measure, but reading error will be there. Okay, write the procedure. Procedure. Write procedure in simple lines. Right. Apply rated voltage. Apply rated voltage to the LV winding. To the LV winding using an auto transformer. Using an auto transformer by observing voltmeter. By observing voltmeter with open circuit on HV side. With open circuit on HV side. With open circuit on HV side. Now read one more time this. So simple in 2 lines or 3 lines. We have completed the exact procedure. We need to apply rated voltage to which winding? LV winding. Using auto transformer, we are applying this by observing voltmeter with open circuit on HV side. That's it. Then take the readings of. Then once voltmeter is rated now. Once voltmeter is rated, which rated? LV winding 200 volts is there. Once the voltmeter is showing that 200, then you need to take remaining 2 readings. That's it. Then take the readings of ammeter and wattmeter. That's it. Take the readings of ammeter and wattmeter. Only single reading. So I'm writing example V naught, I naught, W naught. So 3 readings we take. What is the V naught reading? Rated voltage 200 volts. Then what is the no load current? Small, that is 5 amps. Example we take. And wattmeter reading? Some power. It will measure some power drawn by transformer. Let it is some 50 watts. So only single reading we take from the test. That's it. Okay. Single reading is taken. Voltage, current, power drawn by transformer. Watts, 50 watts. Now we have to go with our objectives. What is the first objective? To find iron loss. So from the readings, you need to find everything now. All the objectives. Okay. Right. First objective. First objective. First one. To find iron loss. To find iron loss. Now, what is the procedure for this? Under this test, the transformer drawing some power, and who is measuring that? Wattmeter will give that power or not? Yes, and that is equal to losses. So write the statement. Under no load, the transformer draws a small power, measured by wattmeter, comma, which is equal to losses. So this transformer will draw some power, and that is measured by the wattmeter, whatever we have placed, and that is equal to what? Losses. Why? Output 0. input we given, and input is output plus losses, but output is 0, so total input equal to losses itself. Therefore, what is the wattmeter reading? Equal to losses. What are the losses? Mainly two losses: iron loss plus a small copper loss. Why a small copper loss? No load it is, small current is flowing only on primary side, so small copper loss also taking place. Now this, we need to find iron loss in this. Therefore, wi equal to the wattmeter reading minus a small copper loss. How to find that small copper loss? I naught square into R1 only. No, copper loss means I square R. What is the current? I naught. Resistance of that LV winding R1. Let, so I naught square R1. So this is the exact equation to find iron loss of transformer. I naught is there in the reading. I naught is there in the reading, but R1 is not there directly. How to find that R1? R1 resistance measurement. Again, you have to do a separate test, and using that you need to calculate resistance. But generally what the people will do in the labs is they will give some value of R1. Let us take some 0.4 or 0.5 like this. They will give some value, and you have to proceed with the value, because Kelvin's double bridge will never work in the lab. Okay. So this is the procedure to find total iron loss, or approximately what we can do. The iron loss is approximately equal to the wattmeter reading. Why? Neglecting small copper loss. Approximately iron loss equal to wattmeter reading by neglecting the small copper loss. This is our first objective. Okay. Next, second objective. Completed. Second. What is the second objective? To find the no load branch parameters. To find no load branch parameters. What are that? R naught and X naught. To find R naught and X naught. How to find R naught and X naught? Now, did you remember we have two approximate circuit? Two approximate circuit. One is first approximate, second approximate. First approximate we use in OC test, I said. Now same circuit we will consider again. Okay, right here. From first approximate circuit. What is the first approximate circuit? If you remember this, R01, X01. So don't draw now. So draw after completion, because I'm showing it is just. This is our first approximate circuit. R naught, X naught. Okay, don't draw this now, because I have to remove this branch. Don't draw now itself. This is our first approximate circuit. R naught, X naught, R01, X01, load. But in this no load test or open circuit test, is there any load? No. So you have to open this. Open. No load on this. If it is open, is any current flow in R01, X01? No current. So as there is no current, is there any use of drawing this R01, X01? No. That's why removing this R01, X01. No use of this. So we have only R naught, X naught. And what is the voltage applied under this test? V naught. Current flowing I naught, and current through this I mu, and this is IW. Now from the figure, tell me what is R naught? Parallel it is. As it is parallel branch, voltage is same for both. So what is the resistance? Voltage by current. X naught, voltage by current. So R naught equal to V naught by IW. Okay, and X naught equal to similarly voltage by current. V naught by I mu. V naught we have from reading. V naught is there. But do you have this IW I mu here? No. But we know the equations for IW I mu in terms of I naught. Tell me what is IW? I naught cos phi naught. Okay, don't forget. In the no load operation, I given these equations IW I mu. And what is I mu similarly? I naught sine phi naught. See, each and everything interlinked. Like the previous no load and load operation, if you don't know, you cannot understand some topics in future. And if you don't know about losses and if you don't know about tests, you cannot understand efficiency voltage regulation next. So each and everything is interlinked. So maybe some of you may attend in some days or may not attend in some 2 3 days. Then definitely if you miss, it will affect the future topics definitely. Now you cannot cover all the topics again. It is very very difficult. If you absent one day also, the next day topics will be difficult again. Okay, so as much as possible, try to complete within the live sessions itself, because you may think if you miss also in recorded session we can watch. Yes, you can watch, no doubt, but the sequence you may miss and you cannot reach again back to the live session. Definitely it is not possible. So as much as possible, try to cover in the live session itself. So I mu is I naught sine phi naught. Now in this equation, I naught we have, V naught we have, V naught we have, I naught we have. But do you have cos phi naught sine phi naught from reading? Directly you don't have. Observe what is the reading. This is W naught is there, V naught is there, I naught is there, but cos phi we don't know. But we can find using the three readings. This is what active power. Power it is Vi cos phi. This is Vi and it is Vi cos phi. So I will equate W naught equal to V naught I naught cos phi naught only. Active power night is. Wattmeter reading is what? Active power. That is Vi cos phi. Now we know W naught, V naught, I naught. The cos phi naught you can find. W naught by V naught I naught. So therefore, I'm writing here using W naught equal to V naught I naught cos phi naught. So cos phi naught we can find from this wattmeter reading by voltmeter reading, ammeter reading. All direct substitution, you will get cos phi value. And sin phi naught. Once you know cos phi naught, sin phi naught also you got, because if you know cos phi naught, what is sin phi naught? Root 1 minus cos square phi. Okay. Now substitute this cos phi sin phi in the IW I mu. First you will get IW I mu and then substitute here. Finally you will get the R naught value and X naught value. So this is the procedure to find R naught X naught. Okay, simple. From circuit we have taken equation R naught and X naught, and from the readings we calculated remaining all. Okay, nothing is difficult. Yes, some of you asking about this auto transformer, the diagram. See this. What is the need of this auto transformer or varier? So problem is those who are in second year, particularly, maybe you have not completed tests also, particularly in this corona pandemic. There is no labs properly, there is no proper studies, nothing is there in engineering colleges, but simply they are giving marks with free of cost to you, and finally they will provide certificates. So much loss for us, it is so much loss. Total education is spoiled, but newly it is we invented like online classes from last year, because of there is no other chance for physical classes right now. But anyhow, this is also a good way to learn. But those who are in second year, for us it is very difficult. Now it is auto transformer. You don't know about auto transformers. How can we show what is the use of auto transformer in lab? Generally, suppose see, this is LV winding, this is HV winding. This is 200 volts I taken. This is 1000 volts. No. Now we need to apply 200 volts. Now tell me, do you have readily 200 volts? Suppose if you switch on any AC board, 200 volts directly will come. No. Suppose if it is single phase, 230 or 220 will come. 200 will not come. Then what is the other way to give the 200 volts? Then we use this auto transformer. Auto transformer is a variable voltage supply. It will give variable voltage source. Generally, two winding transformer, what is the secondary voltage? 1000 only it will give. But auto transformer is not like this. Auto transformer will be variable, means 0 to whatever the rating it is designed, 1000 or 400 or 500, 0 to 400 suppose. It will give 100 volts, or it may give 120, 130, up to 400 volts it may, based on its rating. For that reason, we are using this auto transformer here, because slowly we will apply whatever is required using this. Supply is given to auto transformer first, and secondary output of auto transformer given to this as a source. 200 volts we will apply slowly. Okay. In open circuit test, power factor is less than 0.5. Why? So in previous no load operation, I said no load. In no load operation, power factor is very less than 0.5. Previously, I given in the phasor diagram. While saying about phasor diagram, there I said power factor is very less in no load case. Okay, due to that we are using low power factor meter. Okay. So second objective is this, to find R naught X naught. Now third objective, this is important. Third one important. If you understand this third one, then only you can answer the previous gate question. Question is very easy, but concept if you don't know, you cannot solve. So I will give that question also after this third objective. You need to answer this question. Try to listen carefully. Very easy question, that is. Only thing is you should know the concept here. See, third. What is the third objective? To separate iron loss into hysteresis loss and eddy current loss. We need to separate it. Iron loss we have to separate. How much hysteresis, how much eddy current. See, listen carefully this procedure. Already we have some reading. What is that? Voltmeter reading is there, and ammeter reading. Anyhow, ammeter reading is not required for this case. Wattmeter reading is there. Okay. What is the previous voltmeter reading? Whatever I taken here, same I am taking 250. 200 volt, 50 watts. Okay. 250. Now this is approximately equal to iron loss only, no? Whatever wattmeter reading, that is itself iron loss here. Neglecting small loss. Now frequency is 50 hertz previously. So the main step to separate this iron loss into hysteresis and eddy current is you required a variable voltage, variable frequency source. Variable voltage, variable frequency source is required. Voltage you can change by auto transformer. Frequency will not change there. See, auto transformer what will do? Voltage magnitude you can reduce or increase anything, but frequency will not change. So if you want to change frequency of source, you need a variable voltage, variable frequency source. That is by power electronic devices we take. Power electronics using drives, we can create a variable voltage, variable frequency source. So for this we required mainly a variable voltage and variable frequency source. Frequency source is required. Without this we cannot do this test. Same reason, mostly in the labs they don't conduct this third objective. They don't conduct this third objective because it won't be available most of the labs. Okay, try to concentrate this in your labs whenever it is there in the lab. Okay, this test. The procedure for this is, see, procedure. The procedure to separate iron loss into hysteresis and eddy current loss. Procedure is conduct the test at a variable voltage and variable frequency, or by reducing voltage and frequency both such that V1 by F equal to constant. So listen carefully. I will give readings also to understand clearly so that you don't get any doubt. Write the procedure first. Apply or right here. Conduct the OC test. Conduct the OC test by reducing both voltage and frequency. By reducing both voltage and frequency such that V1 by F equal to constant. Supply voltage to frequency should be constant. Like that, you have to reduce. Conduct the OC test again, reducing both voltage and frequency. You have to reduce voltage and frequency also simultaneously, such that V1 by F equal to constant. So only two readings is enough. Already we did one reading is over, and one more reading you have to do. How? First of all, whenever V1 by F is constant, tell what is the iron loss equation. Iron loss equation. Just now we have seen AF plus BF square. Okay, AF plus BF square. Now from this equation, I will divide the complete equation with frequency. Dividing complete equation with frequency. Now what we get here, A plus B into F. So this is we are getting. Now we will consider that this is of the form, this is y equal to C plus mx. Y equal to mx plus C. Y equal to mx is what? Straight line passing through origin. But what is y equal to mx plus C means? It is the equation of straight line which is not passing through origin. Okay, which is not passing through origin. In the same formula, it is there. This equation Wi by F equal to A plus BF. So I will consider Wi by F means y-axis term. This A means constant C. This B is the slope of the line, and this F is the x-axis. Now what I will do is, previously I conduct one reading at 50 hertz, rated voltage given, and I got some iron loss 50. Now I will calculate this Wi by F. Wi by F. Wi how much? 50. 50 by 50, 1. Okay, some value I got 1 it is. Next, what is the procedure I said? Reduce both voltage and frequency. Now I will reduce the frequency to 25. Then how much voltage I have to reduce? Same, half of the voltage I need to reduce, 100 volts. Why? V1 by F should be same. V1 by F. See, 200 by 50, 100 by 25, same, 4 only. Then here you will get some iron loss. Let it is some 20 watts. Some 20 watts example. 20 watts you got. So after reducing voltage and frequency to new voltage is 100, new frequency is 25. Then I got the iron loss which is measured by wattmeter is 20 watts. Then Wi by F. This is Wi, this is F. Take the ratio Wi by F, 20 by 25. How much? 20 by 25. 0.8. Okay. So only two readings is enough for us. Enough. Why? Straight line it is. This is a straight line. As it is straight line, how many points required to draw this straight line? 2 points. That's why two readings is enough. Now what is our next step is procedure. Procedure is what? First point, conduct the same OC test by reducing both voltage and frequency such that V1 by F equal to constant. So we conducted voltage reduced, frequency also reduced such that V1 by F is same. Then we need to plot a graph between x-axis and y-axis. No? What is y here? Wi by F. What is x means? Frequency. So write that point. So take these values. So this is first point in procedure. Second point. Second. Yes, you can use alternator at reduced speed. Yes, if variable voltage, variable frequency source is not available, then you can use alternator. Okay. Right. Second point in procedure. Second, draw a graph between draw a graph between Wi by F and frequency, comma, which is a straight line, which is a straight line, which is a straight line, not passing through origin, not passing through, not passing through origin, not passing through origin. So we are drawing the graph. Observe y-axis, x-axis. What is y-axis means? Wi by F is the y-axis term. Wi by F. It is y-axis term. And what is x-axis means? Frequency variation is the x-axis. Now we have readings here. Wi by F and F. These two we have to draw. At 50 hertz, what is the value of Wi by F? 1. So let this is 0, 25 hertz, 50 hertz. Okay. At 50 hertz, this is at 0.4, 0.8. This is 1. This is 1. At 50 hertz, it is 1. At 50 hertz, the value of Wi by F is 1. Next, at 25 hertz, the value of Wi by F is 0.8. So I indicate 0.8 here. This is 0.8. 0.8. Now join these two lines and extend the same line up to the, join these two lines. Extend wherever it will touch y-axis. Wherever this straight line cuts the y-axis, what is that value? So this value is nothing but which value it is? C. Now in straight line y equal to mx plus c, wherever it will cut the y-axis, that is C value. So similarly, C means what here? A. Constant A. The main aim of this third objective is to find A and B, the constants A and B. So once you know the constants A and B, you can find hysteresis eddy current at any frequency. Hysteresis loss is what? AF. Eddy current loss is what? EF square. That AB we are calculating in this third one mainly. For that we are drawing a graph between this Wi by F, this Wi by F and frequency. Okay. So if you draw, you will get the AB values like this. So wherever it will touch, this is the constant A. This value is nothing but A. So you will take some scale here, 1 centimeter, some 0.4, 0.4 like that. So wherever it will touch, you will take that value, that is A. And how to find slope of the line? What is the slope of the line? M. M is nothing but B. M is nothing but B. B is what? Slope. M is the slope. So with respect to our line, if you compare, B is the slope here. So if you find this angle theta, then apply tan theta, which is slope of the line, no? Slope of the line, that is nothing but constant B. So B value you will get. Or other way is what to find the slope of the line? Y2 minus y1 by x2 minus x1. Like this also you can do. You will get slope. That is nothing but B here. So you calculated A value and you calculated B value. Once you know A and B, then therefore hysteresis loss at any frequency is AF. Eddy current loss at any frequency is BF square. Okay, now you will get hysteresis loss and eddy current loss. So if you wanted 50 hertz, substitute F equal to 50. If you substitute F equal to 50, you will get hysteresis separately, eddy current separately. And if you add both, you will get 50 watts. So like that, we can separate iron loss into hysteresis and eddy current. So listen one more time, procedure. So first, OC test we conducted at rated voltage and frequency. There we got some single reading, voltage, current, wattmeter. Now same voltage reading, wattmeter reading I taken, that is at 200 volt 50 hertz frequency. 50 watts is the iron loss. Now in order to separate iron loss into hysteresis eddy current, our procedure is we need to reduce both voltage and frequency such that V1 by F equal to constant. So like that I reduced voltage to 100 volts and I reduced the frequency to 25. V by F is remains same. Then I got one reading, Wi is 20 watts. And we know already from V by F is constant. This is the iron loss equation. Now to this equation, we have divided completely with frequency. Then we got a standard form Y equal to mx plus c. So accordingly, Wi by F we calculated, and we have drawn a graph between Wi by F and frequency. And from the graph, calculate A value and B value. Once you know A, B values, you can find anywhere the hysteresis and eddy current loss. Okay, clear all of you this? If you know about this procedure, then only you can solve that question. Otherwise, if I given that question before this, you cannot attempt anything. Okay, any doubt? This is third objective, to separate iron loss into hysteresis and eddy current loss. Now see the previous question on this. See this question. Read the question. An open circuit test is performed on 50 Hz transformer using variable frequency source, keeping V by F ratio constant. Okay, to separate its eddy current and hysteresis loss. The variation of core loss, iron loss divided by frequency. So what we taken, it is as Wi by F, iron loss by frequency, as a function of frequency shown in figure. So there is a graph given between Wi by F and F frequency. Now we need to find the hysteresis and eddy current losses of transformer at 25 Hz. We need to find the hysteresis and eddy current loss at 25 Hz. How to find hysteresis and eddy current at 25? What is the formula for hysteresis? AF. And eddy current loss is BF square. So at 25 we can substitute, but AB unknown for us. That AB you can calculate from graph. What is A? Tell me directly here. What is A from the figure? Wherever that graph will touch the y-axis, this value itself A. So A is directly 10. A is directly 10. A value we have. Now find the B value, slope of the graph. Some of you asking, without this graph, why can't we find this hysteresis eddy current just like previous problems? So try to understand here. Here in these questions, you have data, open circuit test data is there. Then with the data, how can you find iron loss? That is hysteresis and eddy current like previous problems. Observe in previous problem, you have iron loss in two cases. There you calculated AB values by solving. But suppose that just it is given, OC test data given, open circuit test data. Now only from test data, how can you find iron loss? That is hysteresis and eddy current loss directly. Okay. So based on the question, we have to proceed. So this is the way to calculate the losses from test data. Previously, directly question is given, variation of iron loss with different voltages and frequency. There we calculated. So B value here we need to find. B value, how it is observed. B value, simple. Take the slope of this line. Slope. This is y-axis variation, 10 to 15. This is x-axis variation. What is this frequency here? 50 hertz. This is given at 50 hertz now. This point is 50 hertz. Okay. So B equal to y2 minus y1. Y2, y-axis. Y2 minus y1 means 15 minus 10 divided by x2 minus x1. X2 means 50. X1 means 0. Now how much it is? 15 minus 10 is 5 by 50. 1 by 10, 0.1. So B value is 0.1, A value is 10. Now once you know A value, B value, now you can find hysteresis eddy current anywhere. Now substitute here. 10 into 25, 250 watts. BF square, 0.1 into 25 square, 625 into 0.1, 62.5 watts. So what is hysteresis loss? 250. Eddy current loss? 62.5. So answer is option B. Okay. BF 15 minus 10. Again, you have to find B now by substituting frequency. This peak value x-axis value is 50 because read the question. Open circuit test is performed on 50 hertz transformer to separate its hysteresis and eddy current loss. So that is at 50 hertz only. This peak value is at 50 hertz. Okay. This is the procedure to find hysteresis eddy current from the graph. Clear all of you this question? See in the graph BF equal to 5. Like that also you can find BF equal to 5 now. Then what is B? 5 by 50. Because frequency 50 hertz, no, they conducted 5 by 50, 1 by 10, 0.1. Okay. Next question. Next question. See this question. When a 20 kVA, so read the question first. Okay, anyhow, by today we complete only OC. Tomorrow only we see short circuit test. Okay, so first complete this question. So important model. So definitely you will get confused in this question. When a 20 kVA 3300 by 220 volt 50 hertz transformer is operated on rated voltage at no load, its power input is 160 watts. Now what is this 160? Under no load, its power input. Under no load, whatever the power drawn by transformer, it is what? Loss. Which loss mainly under no load? Iron loss. So iron loss is given 160 watts at a power factor 0.15. Okay, whatever, less than 0.5 it is. Under rated load condition, the voltage drop in total resistance and total reactance means percentage R given 1%, percentage X given 3%. Percentage R 1%, percentage X given 3%. The question is the input power when the transformer delivers means what? Output power, no? It is, yes, transformer output power is given. How much it is? 14.96 kilowatt at voltage 220 volt, and power factor of the load is 0.8 lagging, 0.8 power factor lag. Okay, on LV side it is. Now what we have to find? Input power. The input power when the transformer delivers this much output, so we have to find input power. So it's very easy question, right? It is input power. How to find input power? Output power plus losses. What are the main losses? Iron loss plus copper loss. Iron loss directly given, and copper loss given or not? Tell me, copper loss given in the question or not? Hmm. Copper loss, yes, given percentage R itself copper loss. So already I said previously, when there is percentage R in the question means there is a percentage copper loss. From here you can find copper loss. Okay, from here you can find copper loss of transformer. Now try to find this. Definitely you will get wrong. Try to find, you will get wrong. So what you did wrong, then I will tell. Find input power, output power 14.96 plus add these two losses, iron loss, copper loss. So first calculate copper loss. We solved yesterday one question how to find copper loss from percentage R. Therefore that try to find copper loss, add here. Definitely you will get wrong, no doubt. Then we will see where you did mistake. Anybody, how much you got answer? Anybody got the answer? How much is the input power? Input power. Output is there already 14.96 K plus losses, that already iron loss is there directly. Only thing is copper loss you need to find. Copper loss. Yes, Gopal Krishna, little you approached. Yes, right. No, not 15,153. Check one more time. No. Yes, Sai Sandeep also, you also little approached. Copper loss 200, but if you substitute that 200 directly, your answers are wrong. You should not substitute. That is the twist in this question. See, percentage or calculation. Iron loss is there. This is fixed. Iron loss never changes. Whatever the load on transformer, 160 only. Output power also given 14.96. So we know percentage R equal to percentage copper loss. Okay. What is the formula for this? Full load copper loss divided by volt ampere rating of transformer into 100. What is the percentage or percentage copper loss? 1 divided by 1 equal to full load copper loss by rating of transformer is there 20 kVA. 20 into 10 cube into 100. Therefore, the full load copper loss of transformer is 200 watts. Okay, full load copper loss. But if you substitute in these losses, what is total input power? Output plus iron loss plus copper loss. So output power they given directly 14.96 kilowatts plus iron loss. What is iron loss? 160. It is fixed. Copper loss. So don't substitute 200 here because this is full load copper loss. Is it given in the question? This 14.96 is the full load output. Is it given? Nothing is mentioned. Some power is given at some voltage and power factor. That's it. And it is not mentioned in the question. It is at full load condition because copper loss is variable loss or not. Yes. Then how can you substitute 200 directly? So you don't know first where transformer operating. Is it operating at full load or is it operating at 70%, 80%, 90%, where it is not given? So this is your duty to calculate first. Now, first from the given voltage and power rating, secondary side voltage is how much? 220 now. Secondary voltage 220. Now you find what is the rated current on LV side first. Okay, first rated current on rated current or full load current I2. Secondary side rated current. How to find? Volt ampere rating divided by secondary voltage. What is the volt ampere rating? 20 into 10 cube divided by secondary voltage 220. How much it is? This is full load current 20K by 220. 90.9 amperes. This is the full load current. Okay, this is full load current. For this much full load current, what is the copper loss? Full load copper loss, that is 200 watts people. Okay, now you need to find with respect to given output power what is the current I2. So given output is how much? Output 14.96 96 kilowatts. Power is always VI cos phi. No? So secondary voltage E2 I2 cos phi. Now substitute here 14.96 into 10 cube equal to E2 secondary voltage 220 given, and voltage current we need to calculate how much it is at that time. Power factor also they given 0.8. Now from this equation find what is the current transformer delivering. 14.96 10 cube divided by 220 into 0.8. Okay, how much it is it 85? All of you got same 85. This is the current transformer delivers. So for the given output power, this is the current it is delivering. But what is the full load current? 90.9. For that 90.9, this is 200. Now we need to find copper loss for 85 amperes. What is the formula? See, for a current of 90.9 ampere, what is the copper loss? How much? 200 watts. Okay. Now for a current of, let I1, this is 1, this is 2. We need to find for a current of 85 amperes. What is the copper loss? How to find? We know copper loss proportional to square of current. Okay, yesterday also I solved one question proportional to current. No, then copper loss in second case divided by copper loss in first case. Second case means what is the current? I2 square, that is 85 square divided by 90.9 square. Now copper loss in second case 200 into 85 square by 90.9 square. See, nothing here, there is no big calculation. Only thing is we are calculating copper loss for the given load. That's it. Okay. Now find here 200 into 85 square divided by 90.9 square. This is I'm getting 174.8788. Is it right? Check. 174.88 I got. This is the copper loss for the given load. Now this copper loss you have to substitute there. Okay, substitute this copper loss. Therefore, how much it is? 174.88. 174.88. Now add all this 14.96 10 cube plus 160 plus 174.88. So this is 15.294.8 watts. This is the input power of transformer. Okay, this is input power. Simple question. Input power you need to find for the given output power by substituting losses. The only calculation is regarding copper loss. Okay, so all of you got same. Yes, good. Okay, all of you complete. 15294.8. Option B is correct. See, almost all values are nearby only in 15 range. So you must do the calculation perfectly. By mistake, if you substitute wrong, here 200 in place of that 174, your answer will be wrong, because that is the copper loss from percentage or whatever we get, always full load copper loss, and we calculated the copper loss for the given load. That's it. Okay. Okay. Now lastly, make a note regarding OC test. So with this we stop here. Right, make a note. Completed all of you this question. Make a note. note. So this point like a question itself, so I will tell this one question, so you try to analyze same as it is the other possibilities. Okay, right. In a transformer, under no load, under no load under no load test, under no load test, by keeping voltage constant, voltage constant, if the frequency decreases, if the frequency decreases, then the no load power factor of transformer is dash. No load power factor of transformer is dash. Increase, decrease, remains same. Under no load test or OC test, by keeping voltage constant. Now I will keep voltage constant. If the frequency decreases, what happens to no load power factor of transformer? It will increase or it will decrease or it remains same. The most important types of question for every examination, it is theory question, but so much analysis required, like good analysis required, otherwise directly you cannot answer. No doubt, directly you cannot answer. You should have some idea of that losses, iron loss, hysteresis loss and eddy current loss, then easily you can solve this. See, so simple one, no need to get struggle for this, very easy. Observe, initially there is some voltage and there is some frequency. We know flux density always proportional to V1 by F ratio. Okay, now there is some voltage previous, there is some frequency previous. Now for this you need to draw the no load phasor diagram. V1, there is some magnetizing current initially and there is some iron loss current initially. Okay, the sum of these two we call no load current, and this is no load power factor angle phi naught. This is what no load power factor angle, and if you apply cosine to this cos phi naught, this is called no load power factor. Okay, no load power factor. Now my question here is, I will keep voltage constant. I am considering voltage constant if the supply frequency decrease. If the supply frequency decrease, what happens to this power factor? It remains same. Power factor means you need to check angle, what happened first. The angle depends on I mu IW, so you have to check what happens to I mu IW. So observe here, so I'm telling directly, it is observe, whenever frequency is reducing, what is the flux density? Increases beyond maximum. Already it is at maximum limit, now beyond its limit, saturation. Due to that, whenever flux density increases means flux is trying to increase, so magnetizing current also increase. Okay, this is first step. If Bm increasing means magnetizing current increasing. Bm increasing means which one increasing? Flux. So I mu also increasing. So I mu increases. Now check what happens to IW. IW depends on hysteresis loss plus eddy current loss. Okay, iron loss total. Now which case it is? V1 constant, frequency only variation. Second case. So in second case, WH proportional to V1 power 1.6 by F power 0.6 and eddy current proportional to V1 square. Okay, now what happened? Check. Voltage constant, frequency reduced. Then what is the hysteresis loss? Little increase, because just F power 0.6, little hysteresis loss increase. Okay, frequency voltage constant, only frequency. So as voltage constant, eddy current loss remains same, no change. So what is overall iron loss now? Slightly increases, slightly, not very high, slight iron loss increase. So what is IW term? Slightly increase. Okay, now whatever changes you got, substitute in the figure. So I'm substituting here. I mu so much increases. New current is this. because of this variation. IW slightly increases. Now draw the resultant. If you draw the resultant, see, this is the new no load current. Now what happens to angle, power factor angle? This is V1 I naught. Angle increases, no? Previously this is the angle phi naught, but now angle increases. So phi naught is increased. If the angle increase, therefore angle increases. Then what is cos phi naught? Decreases. No load power factor of transformer reduces. Okay. So this type of questions you can answer only by drawing this diagram. Otherwise, you cannot answer. You need what is the variation of IMU, and you need what happens to IW. Then you can answer the final power factor. So what is the power factor finally? Decreases. By keeping voltage constant, if the frequency decrease, the no load power factor decreases. So right here, no load power factor decreases. So like this type of variations you can build. Now in second point, you consider second point, by reducing both voltage and frequency, such that V1 by F equal to constant. What is the no load power factor? So you try to analyze this. Both reduce, voltage reduce, frequency reduce, such that V1 by F is constant. What happens to no load power factor? Okay, you try to answer this question. So take this. So with this we stop today, and tomorrow we continue short circuit test. Okay, tomorrow 5 to 9 p.m. evening.
Sir,
Tell me.
sir, స్టాకర్స్ అంటే ఏంటి సార్?
ఏంటి?
హమ్మింగ్ నాయిస్ వచ్చినప్పుడు మీరే చెప్పారు కదా సార్.
Staggering means the process of joining laminations ని staggering అంటాం కదా.
సార్ ఒకసారి మళ్ళీ చెప్పరా?
Process of attaching all laminations together. Suppose ఆ ప్లేట్స్ అన్నిటిని మనం అటాచ్ చేయాలి కదా.
ఓకే.
ఆ థిన్ ప్లేట్స్ ని, ఆ ప్రాసెస్ ని స్టాగర్ అంటే జాయినింగ్. అవి ప్రాపర్ టైట్ గా అటాచ్ చేయాలి. స్టాగరింగ్ అనేది పర్ఫెక్ట్ గా లేకపోతే మనకి ఛాన్సెస్ ఆఫ్ ఎయిర్ గ్యాప్స్. ఆల్రెడీ వి హావ్ సీన్ నా కోర్ స్టాగరింగ్ కాన్సెప్ట్ ప్రీవియస్.
ఒకసారి డీసీ కిక్ ఓపెన్ చేయరా సార్? డీసీ కిక్ టెస్ట్. సారీ.
నెంబర్
డీసీ కిక్ టెస్ట్ నాకు తెలియదు చూసుకోలేదు నెంబర్. సార్ ఇక్కడ మీరు ఏం చెప్పారంటే డీసీ కరెంట్ అనేది మనం యూజ్ చేయం కదా సార్, ఎక్కువసేపు మనం యూజ్ చేయలేము కదా సార్. అయితే అప్పుడు మీరు ఏమన్నారు అంటే ప్రొటెక్షన్ వైజ్ పెట్టుకొని యూజ్ చేయొచ్చు అని చెప్పారు కదా సార్. ప్రొటెక్షన్ డివైసెస్ అంటే ఏమేం డివైసెస్ యూజ్ చేయాలి సార్?
స్విచ్ ఓన్లీ, బికాస్ బై యూజింగ్ దిస్ స్విచ్ మనం జస్ట్ క్లోజ్ చేస్తున్నాం అండ్ ఓపెన్ చేస్తున్నాం కదా సేమ్ టైం. జస్ట్ ఒక ఫ్రాక్షన్ ఆఫ్ సెకండ్ లోనే, జస్ట్ 1 సెకండ్ లో క్లోజింగ్ అండ్ ఓపెన్.
ఓకే.
అదర్వైజ్ ఇది లేకపోతే ఏమవుతుంది, డైరెక్ట్ సప్లై వెళ్తూనే ఉంటుంది కదా. మనం ఈ DC వోల్టేజ్ రిమూవ్ చేసేంత వరకు కరెంట్ విల్ బి దేర్. బట్ ఇఫ్ దేర్ ఈస్ ఏ స్విచ్, ఇమీడియట్లీ యూ కెన్ ఓపెన్. So that is itself we are protecting transformer from continuous DC supply.
Sir, ఇంకొకటి సార్ 74F సార్. దాని తర్వాతకి సార్. సార్ ఇక్కడ డిక్రీజ్ అయినప్పుడు మీరు ఎలా తీసుకున్నారో అర్థం కాలేదు సార్. అంటే 10% డిక్రీజ్ అవుతుంది అంటే మైనస్ చేస్తున్నారా? అంటే దేని నుంచి ఎట్లా చేస్తున్నారో అర్థం
To
కాలేదు.
initially frequency f1 equal to f. Okay.
ఓకే సార్.
Now frequency 10% reduce అయింది. Means what is the 10% of f? 10% 0.1 f కదా.
ఎస్ సార్.
అంటే ఈ f లో ఆ 10% ని తీసేయండి. How much? 0.9 f.
ఓకే. అంటే ఇంతకు ముందుకు దానికి ఇంక్రీజ్ అన్నప్పుడు 1 తీసుకున్నాం కదా సార్.
దేర్ ఆల్సో సేమ్ f. అక్కడ ప్లస్ 10% కదా 0.1 f యాడ్ చేస్తున్నాం కదా. ఇంక్రీజ్ 1.1.
ఓకే సార్.
నెక్స్ట్. హలో.
Hello, sir.
Tell me.
Sir, last problem. Last one. Sir, explain, sir, first and total one.
Whenever frequency reduce, what happens to density increases? Okay, density increase means what? Flux increasing only, no?
Sir, starting to, sir. I can't understand, sir.
Starting means ide kada starting. So initially there is some voltage and frequency initial ga.
Yes, sir.
At that time we have drawn the phasor diagram, these black lines. Okay, I mu, I w, I naught. There is
Yes,
some
sir.
angle phi naught.
Yes,
Now
sir.
whenever frequency is reduced by keeping voltage constant, what happens to density increases? No. Density increase means flux is increasing now. What is the actual flux density? Flux per area.
Yes, sir.
Density increase means flux increase. So when flux will increase actually? Whenever current increases. Which current is responsible for flux? Magnetizing current. Because of that I mu increases. And IW దేని మీద డిపెండ్ అవుతుంది? ఐరన్ లాస్. ఐరన్ లాస్ WHWE కదా, అది మనం సపరేట్ క్యాలిక్యులేట్ చేస్తాం. ఐరన్ లాస్ ఏమవుతుంది? ఓవరాల్ లిటిల్ ఇంక్రీజ్ అవుతుంది. దెన్ IW స్లైట్లీ ఇంక్రీజ్ అయింది. దెన్ వాట్ ఎవర్ చేంజెస్ వి గాట్, అదే చేంజెస్ ని మనం ఫిగర్ లో అప్లై చేస్తున్నాం. IMU ఇంక్రీజ్ వెరీ మచ్. ఓకే, అండ్ IW స్లైట్లీ ఇంక్రీజ్. దెన్ రిజల్టెంట్ డ్రా చేస్తే మనకి యాంగిల్ ఏమైంది? ఇంక్రీజ్ అయింది.
Decrease in.
పవర్ ఫ్యాక్టర్ డిక్రీజ్ అవుతుంది.
Yes, sir.
ఓకే
సార్ ఇంకొకటి ఏంటంటే సార్, వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ డిక్రీజ్ అయినప్పుడు సేమ్ టైమ్ లో డిక్రీజ్ అయినప్పుడు కాన్స్టెంట్, యాజ్ వెల్ యాజ్ ఇంక్రీజ్ అయినప్పుడు కూడా కాన్స్టెంట్ సార్ వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ?
బోత్ వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ. సెకండ్ క్వశ్చన్, సెకండ్ పాయింట్.
సార్ ఇంతకు ముందు వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ బోత్ డిక్రీజ్ అయినప్పుడు కాన్స్టెంట్ అన్నారు కదా సార్. ఇక్కడ
ఏం కాన్స్టెంట్?
వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ
బోత్ రెడ్యూస్ అయితే
కాన్స్టెంట్ అన్నారు కదా సార్.
V1/F రేషియో కాన్స్టెంట్.
యాజ్ వెల్ యాజ్ ఇన్ కేస్ వోల్టేజ్ అండ్ ఫ్రీక్వెన్సీ బోత్ ఇంక్రీజ్ అయితే సార్,
then also proportionally both will increase kada, then also it is constant only.
Okay sir.
Ante they should mention that word, otherwise if voltage increased by 10%, frequency increased by 5%, then it is not constant. Proportionally both increase such that V1/F is constant, then it is correct.
Okay sir. Okay, thank you sir.
Sir, good evening sir.
Tell me Charan.
Sir, you told V1 and F, if both increases proportionally with a constant proportion, then BM is also constant, sir.
Yes, constant.
Sir, in after total iron losses, sir, some one problem, sir. That nominal voltage
should remember slide number.
After break, sir. 4 break, 4 PM.
Question. This one.
No, sir, the 2500 watts and 440 volts.
Should remember the slide.
After iron losses, total iron losses, sixth problem, sir. This one only, sir.
This one, gate 21 question, no? It is gate 21 this year.
Sir, I did not understand this one, sir.
This is same as previous question only, no? So given iron loss at two different voltages and frequencies, okay?
Okay, sir.
Then we have to find at nominal voltage and frequency the hysteresis and eddy current loss. Nominal voltage means which one? They mentioned already here, observe. The iron loss is 2500 at nominal voltage and frequency. Means which is the nominal voltage and frequency? 440, 50 hertz. Same we calculated.
Okay, sir. I am confused with this nominal voltage, that one only, sir.
That is given already there. Okay.
Generally, nominal voltage means what, sir? What they
Nominal
give?
means rated, but here they mentioned this is as nominal, no? So we taken same.
Okay, sir.
Sir,
Tell me.
మనము ఇది ఇక్కడ ఓపెన్ సర్క్యూట్ టెస్ట్ ఉంది కదా సార్, దాంట్లో ఎల్వి సైడ్ తీసుకోవాలని చెప్పారు కదా సార్. అంటే ఎందుకు తీసుకోవాలి సార్ ఎల్వి సైడ్? హెచ్వి సైడ్ కన్నా ఎల్వి సైడ్ ఎక్కువ కరెంట్ ఇస్తుంది అన్నందుక?
That is some advantage while measuring ammeter current. In the ammeter మనకు accurate reading వచ్చే ఛాన్స్ ఉంది కదా, because LV side what is the rated no load current? Little higher.
Yes,
that high current we can measure little. Already no load current is a small current, so a small current low LV side the current is little higher kada when compared to HV side. So that current we can measure accurately when compared to HV. అందుకే మనం ప్రిఫర్ చేస్తాం.
హెచ్వి సైడ్ ఓపెన్ చేసి అప్పుడు ఏమవుతుంది సార్? హెచ్వి సైడ్ కనెక్ట్ చేసుకుంటే
HV side source ఇచ్చి LV ని ఓపెన్ చేయండి, then also you can do the test. But there ammeter what is the current will flow? No load current very small kada.
Yes sir.
Then you need to measure accurately means it is may not be possible ఎందుకంటే no load current very small compared to LV side. So accurate readings రావాలంటే కొంచెం వాల్యూ ఎక్కువ ఉండాలి, మరి తక్కువ ఉన్న కష్టం.
Don't speak, I'm unready.
Okay sir. సార్ డైఎలక్ట్రిక్ స్ట్రెంగ్త్ ఎందుకు అంటే యూజెస్ ఏంటి సార్? యూజ్ చేస్తున్నాం కదా డైఎలక్ట్రిక్ స్ట్రెంగ్త్. డైఎలక్ట్రిక్ స్ట్రెంగ్త్ యూజ్ చేసినప్పుడు దాని వల్ల యూజెస్ ఏంటి సార్?
That is insulator kada, which will insulate two bodies, LV and HV windings, because LV winding HV winding should not contact each other because they may get short, no? Two different voltages. So to avoid that short circuit of winding we place insulator there.
Okay sir, thank you sir.
Tell Budvi.
Hello sir.
Tell me.
Sir, to separate iron losses into WH and WA, you said a method na sir. Sir, same method మా కాలేజ్ లో కూడా చేసాం సార్, సేమ్ ఇదే మెథడ్ లో చేసాం, గ్రాఫ్ మెథడ్. అయితే నా డౌట్ ఏంటంటే సార్, వేరియబుల్ వోల్టేజ్ వేరియబుల్ ఫ్రీక్వెన్సీ కాకుండా ఓన్లీ వోల్టేజ్ ఒకటి తగ్గించి కూడా చేయొచ్చు కదా సార్?
No, it won't come because frequency should reduce kada for that condition. To draw the graph frequency should reduce, otherwise straight line how will get?
సార్ నాకేమనిపించిందంటే 50 హెచ్ దగ్గరే పెట్టి వోల్టేజ్ తగ్గించి తీసుకుంటే అప్పుడు అది కేస్ 2 లో ఫాలో అవుతుంది కదా సార్? కేస్ 2 లో సాల్వ్
then you will get like a parabola shape, that is.
ఓకే సార్,
that is not straight line.
అప్పుడు దాని నుంచి సాల్వ్ చేయలేమంటారా సార్?
No, straight line, if it is straight line then only AB is easy to find. Okay.
And one more doubt sir, after that second question sir.
After that question. Where
when it 20 kVA 300 volts means copper losses not at rated load 14.96 kilowatts.
This one.
Sir. Full load at secondary side we can calculate like this also na sir? means rating into 0.8.
Rating into yes, that is
Full load
KW.
power.
Yes, yes.
KW, sir. Then
yes.
we can directly divide for X value 14.96 by 16. We will directly get X value.
X
From
is,
that we can go for copper losses at output. It will reduce steps.
are you getting same, no?
Same, sir.
Then write on that.
Okay, sir.
That is also correct, but
Yes,
actually the current rating always we find from volt ampere rating, because KW.
Yes, sir, but power factor doesn't put any thing on that, sir. That's why we take that
Okay,
way.
you can find like that also, right?
Thank you, sir.
Mr. Mohammed Mabin.
Hello, sir.
Anil, tell me.
Yes, sir. Can you please open the slide 58?
50?
58F, sir.
Is it?
Yes, sir. Sir, మనం ఇక్కడ క్యాలిక్యులేట్ చేస్తాం కదా, క్యాలిక్యులేట్ చేస్తున్నప్పుడు యాక్చువల్లీ హిస్టరీసిస్ మనకి ఫార్ములా చేసినప్పుడు V స్టాండ్స్ ఫర్ వాల్యూమ్ ఆఫ్ ది కోర్ కదా సార్. బట్ మనము V అది ఆ ప్రొపోర్షనల్ చేసినప్పుడు ఆ V బదులు మనం వోల్టేజ్ చేస్తాం, ఎందుకు సార్?
ఇది B కదా, WH ప్రపోర్షనల్ టు BM పవర్ 1.6 ఉంది కదా, ఆ ప్లేస్ లో కదా మనం వోల్టేజ్ రాస్తున్నాం.
అర్థమవులేదు.
Actual WH equal to eta B max power 1.6 FV. This V and eta we are never considering. They are constant,
Yes,
fixed.
we are making
Now in place of BM we are writing V1 by F whole power 1.6 into F. That is
okay, sir. Okay, sir.
Okay, we are not touching volume.
Yes, sir.
Next, Vasu. Sure. Hello.
Hello, sir. The last notes.
Which one? Last problem.
Yes. So, in that, when we told that BM decreases, magnetizing current decreases significantly, sir. But given BM, when we find the magnetizing current, what we do is we look at the BH curve, we map the BM corresponding to the I mu on the x-axis, no, sir. This slope is very steep, no, sir. It's like 10,000 or something. So how would there be a considerable decrease in magnetizing current when there is a decrease in BM, sir?
You are asking second question or first question?
The first question. When you decrease frequency, BM decreases.
BM increases.
Yeah, BM increases, which causes a corresponding increase in.
Yes.
In I mu. I'm asking how does this how does I mu increase rapidly, sir? It's already so small.
See under see, I will draw that figure. Check. Actually, every magnetic material, this is flux variation and current variation, I mu. So whenever current increase, flux increase, and at one of the current saturation, then almost constant it is. This is saturation point. This is the current I mu regarding maximum flux. Okay, maximum flux or maximum density, you can consider it is. But from now, if little flux also increase, what is the increase in current? So much, because it is saturated. After this, the increase in flux is almost negligible, constant, little slightly increase. And what is the current here? Very high increasing.
Oh, okay, sir.
Okay.
Thank you.
సార్ 99F సార్. సార్ ఇక్కడ మనల్ని ఇన్పుట్ పవర్ అట్ 0.8 పవర్ ఫ్యాక్టర్ లాగింగ్ దగ్గర కనుక్కోమన్నారు కదా సార్. అప్పుడు కాపర్ లాస్ ఇక్కడ మనకు ఫుల్ లోడ్ లో తెలిసింది 0.8 లాగింగ్ అంటే ఏంటి 0.8 హోల్ స్క్వేర్ చేసి చేసేయచ్చు.
పవర్ నో ఇది పవర్ ఫ్యాక్టర్ కదా. Not x, it is not fraction of load, it is power factor, that is different. If percentage of load is given, then you can take 0.8 square. Adi power factor kada, not percentage of load.
ఓకే సార్, క్వశ్చన్ మిస్టేక్. సార్ మళ్ళీ పొలారిటీ టెస్ట్ లో ఎందుకు వోల్టేజెస్ అడిషన్ సబ్ట్రాక్షన్ అలా చేస్తున్నాం సార్?
మనం చేయట్లేదు, మనకి పొలారిటీ రావాలి కదా సెకండరీలో. ఆ పొలారిటీ మార్క్ చేయాలంటే ఇది సమ్ అవుతుందా డిఫరెన్స్ అవుతుందా అబ్జర్వ్ చేయాలి. జస్ట్ you should observe either it is sum or difference to mark secondary polarity.
ఏం యూస్ సార్?
యూజ్ ఏం లేదు, సెకండరీ పొలారిటీ మార్క్ చేస్తున్నాం కదా, అది సమ్ ఆ డిఫరెన్స్ బట్టి. అదర్వైజ్ హౌ కెన్ వి మార్క్ సెకండరీ పొలారిటీ? అందుకని Anil Kumar Sagar.
Good evening, sir.
Tell me, Sagar.
Sir, once explain the copper load losses, sir. 79F.
Copper?
79F, sir.
See, generally this copper stray load loss is due to solid conductors. Whenever any conductor is solid, no more surface area available. So when current passing through that, what happened? Whatever current is passing, it will cause some flux around that. That flux will touch same conductor again, which causes some internal EMF induced and then circulating currents. Within the conductor, they will circulate. So these currents we name stray current. Because within the conductor only they rotate. It won't come back to outside. From one end of the conductor to other end, it won't come. Now, it will cause an I square R loss. That is itself copper stray load loss.
Okay, sir. It cuts the same flux of the same conductor.
Yes, same flux, same conductor, same current. Within that, it won't come outside.
Okay, sir. Thank you, sir.
Good evening, sir.
Tell Amit Vikram.
Sir, the voltmeter, analog voltmeter and ammeter that we are like for voltmeter, you just mentioned that the maximum limit which you can calculate which you can take the voltage reading is up to 600 voltage. So in generating stations and in
they don't use that. There we have digital or clamp meters. Digital meters will be available, no? There.
Okay, sir. So they are not based on moving coil or moving iron.
No. They don't use these meters there. They're completely different. High rating, digital, completely digital only.
Okay, sir.
Next, still anybody?
Hello, sir.
Sure.
Sir, 99F, sir. Sir, 99F, sir. A problem, sir. Explain.
Yeah. Which one? This one?
99. Yes, sir.
Here we need to find input power. So generally input power is output power plus losses kada. So they given output 14.96. So you manam input power calculate cheyali. So input power is what? Output plus losses. So losses lo mainly iron and copper. Iron loss also directly given 160.
Yes, sir.
Then copper loss we can find from percentage R. We have formula, no? Percentage R equal to percentage copper loss. Full load copper loss by rating. So from that we got 200. But according to given output, it is not full load current. Actually, full load current how much? 90.9. From the transformer data we calculated. But according to given output, we got I2 is only 85.
Yes, sir.
So for full load 90.9, copper loss 200 aithe. For 85 amps, copper loss will reduce or not? reduce. And the current reduces, copper loss also reduce. So that copper loss we calculated using this relation, and that is substituted in that input power. Okay. Simple question, just input power calculation.
Okay, sir. Okay, thank you, sir.
Hello, sir.
Siva, tell me.
In polarity test, why should we apply rated voltage, sir?
Any voltage you can apply.
So the drawback is if you use high voltage, if you use
But
10 kV.
for high voltage rating transformer, if you apply very low voltage, that may not be sufficient for that heavy winding. Then you need at least from little high voltage only. For small voltage, no problem.
Okay, sir.
Next, anybody? Okay, so I'm closing for today. Tomorrow.